what this quantum world is all about. Welcome, each one of you, to Quantum Dialogue 2026. Let me begin with a simple thought. Most of us have grown up learning that the world follows predictable rules, that an object is either here or there, that a door is either opened or closed, that a coin lands either heads or tails. But quantum science tells us something deeply surprising. A particle may be in two places at once. Information can be shared instantaneously across vast distances. And a problem that would take the fastest classical computer millions of years to solve might be cracked in minutes by a quantum computer. This is not science fiction. This is a frontier that we are standing at right now in 2026. India is stepping boldly into this space with National Quantum Mission and growing collaboration between our leading institutions. We are actively engaged in shaping this global revolution. This is precisely the spirit which brings us here. As a student entering this formidable yet beautiful edifice of quantum thought, there have been many occasions when we have experienced sudden realization, a spark, an internal leap, by the way of brainstorming and animated exchanges. I would like to imagine that the quantum dialogue will bring this experience to all of you. In the end, I would like to quote Helen Keller. Alone, we can do so little. Together, we can do so much. Let's begin the Quantum Dialogue 2026. I would now like to welcome our dignitaries on the dais for lamp lighting, prayer, and followed by Maharashtra Geet. I would like to welcome Professor Sudhir Ranjan Jain, Dr. Suresh Ukrande, our director, Dr. Ajay Kapoor, our vice chancellor, and our chief guest, Mr. Sandeep P. Trivedi. Now we proceed for the lamp lighting. Now we would proceed with the Somaya prayer, followed by the Maharashtra Geet.
पूर्णमदः पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते ॐ ईशावास्यमिदं सर्वं यत्किञ्चिच्चक्यां जगत् तेन त्यक्तेन भुञ्जीथा मा गृधः कस्य कृद्धनम् मूकं करोति वाचालं पङ्गुं लङ्घयते गिरिं यत्कृपातमहं वन्दे परमानन्दमाधवम् ॐ प्रणो देवी सरस्वती वाजेभिर्वाजिनीवती वीणामविद्यवतु ॐ चोदयित्री सूनृतानां चेतन्ती सुमतीनां यज्ञं दधे सरस्वती ॐ असतो मा सत्समय तमसो मा ज्योतिर्गमय मृत्योर्मा अमृतं गमय ॐ सहना भवतु सहनौ भुनस्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै सर्वेऽत्र सुखिनः सन्तु सर्वे सन्तु निरामयाः सर्वे भद्राणि पश्यन्तु मा कश्चित् दुःखमाप्नुयात् ॐ शान्ति शान्ति
सह्याद्रीचा सिंह गर्जत शिवशंभू राजा
दरी दरीतून नाद गुंजला महाराष्ट्र माझा
जय महाराष्ट्र माझा जय जय महाराष्ट्र माझा काळ्या छातीवरी कोरली अभिमानाची लेणी शिवला निधळाच्या घामाने भिजला देश गौरवासाठी झिजला दिल्लीचे ही दस्तगाठी महाराष्ट्र माझा जय महाराष्ट्र माझा गरजा महाराष्ट्र माझा जय जय महाराष्ट्र माझा
Now I would like to invite Mr. Sudhir Ranjan Jain to start the quantum dialogue with a few words.
Good morning, everyone. It's so beautiful to see everybody here, all friends from old times, my new friends, which I have made in last approximately 1 year. Some of my dear old friends here, and Professor Ajay Kapoor, the Vice Chancellor, Dr. Okarande, Director of the School of Engineering, my very dearest colleagues who have traveled from Pune and BRC, Tata Consultancy, around 20 institutions representing this hall at this time. It's very nice for me to welcome you all here. We are in this process of a very long journey. The journey which started with thoughts of analytical engine, making of an analytical engine, the old computers made by Charles Babbage. You can see that in certain museums now in some pictures. And from those times when people thought that writing a code, a simple code, by adding numbers itself, cranking gears and levers, etc., was such a formidable task, to this generation where we are using artificial intelligence, quantum AI, and ideas like that to shape our thoughts and bringing more security at all levels in our life, at the level of our nation, and so on. We are trying to establish a program of quantum computing, quantum information science at Somaiya Vidyavihar University, and I'm very happy to help the system try to do this. And there is, of course, tremendous support from the faculty, students, all the senior leading staff, and it's so much easier to do everything. This event, I thought, as Astha said, that there are so many times that we have felt that by mere conversations and brainstorming and having frank discussions which are not articulated very precisely in terms of equations or arguments or theorems, there is a pre-discussion of all that which happens with brainstorming, ideas exchanged, making mistakes, laughing at mistakes, and learning from them and evolving from them. And here, so I invited a set of people who have in their own journeys been very special, and I've known them for such a long time that I know that they can bring this conversation alive. And so I'm very happy that all of them are here and all of you are here. And with those words, I just wish all of us succeed in establishing this dialogue, this quantum conversation, and learn from all the interaction that we have here. I thank you all. Thank you very much.
Now I would like to welcome our Director, Sir, KJ Somaiya School of Engineering, Dr. S.K. Ukhrande, to please come and give a few words.
Yeah, good morning to all of you. Good morning to all of you. Yeah. Chief guest of today's function, Dr. Trivedi, former director of TIFR, our Vice Chancellor, Professor Ajay Kapoor, Dr. Sudhir Ranjan Jain, Professor of Eminence at KJ Somaiya School of Engineering, faculty members from KJ Somaiya School of Engineering and Somaiya Vidyavihar University, and participants from all other institutions to this quantum conclave. On behalf of management, I welcome you all to this one-day event called Quantum Dialogue. Let me brief about the Somaiya Vidyavihar and then Somaiya Vidyavihar University and KJ Somaiya School of Engineering brief. This Somaiya Vidyavihar has a legacy of more than 8 decades. Right, started in 1942 with a school in Kupargaon in Ahilyanagar district, and this campus started establishing from 1959 onwards. And you see around in the campus, such a beautiful campus, there are various institutions, engineering, management, arts, science, commerce, School of Design, Dharma Studies, Sports, and many more. They were started establishing right from 1959 onwards, and from 2019 onwards, many institutions on this campus, major of the institutions are under the umbrella of Somaiya Vidyavihara University. As far as Somaiya Vidyavihara is concerned, which has 40 plus institutions with 3,000 plus faculty and staff members and 40,000 plus students, right from school to PhD. In campuses, in this campus Vidyavihar, other campus at Ayurvihar, then campus in Ahilanagar district in Maharashtra, in Karnataka, in Gujarat, Kutch, and in Madhya Pradesh as well. So total 40,000 plus students are taking education, right from school to PhD. Now about the Vidyavihara University, Somaiya Vidyavihara University, which is led by our Vice Chancellor, Professor Ajay Kapoor. We are working and growing every day. And as I told, 16 institutions are there under this umbrella of Somaiya Vidyavihara University. Majorly it's engineering, management, and 14 plus few other institutions. This KJ Somaiya School of Engineering started in 1983 with 5 disciplines, and today, right now, we have 10 BTech programs, 9 MTech programs, and 6 PhD programs. I will not go in details of naming each and every program, but we have approximately 3,800 plus students in UG, PG, and PhD together, and maybe next year we'll be crossing 4,000 students on roll. So it's a big institutions, and a lot of strong academics, and a lot of research is happening in various domains. Now, role of any institution, any university is to create knowledge and disseminate knowledge. So majorly this institution is for the academic institution, academic university, but we are trying hard to make it academic plus research institute, research university. And our management is very proactive in starting the courses which are required, in which human resource manpower is required in the industry. Like, I'll give the example. BTech, we have many programs like computer and communication engineering is there, robotics and AI is there, and VLSI design technology is there, and basic courses, mechanical, computer, IT are already there. But these courses, interdisciplinary courses are there at UG and PG level. Now at PG level, we have started one program 2 years back, that is agricultural science technology. Unique program started by engineering college in the agricultural domain. That shows the vision of our management. It's not only traditional courses and give the education, create a manpower for industry or society, but start something new. And this quantum, today's program, Quantum Dialogue, we have thought process, management has thought process to start new programs like quantum computing and information science. From this academic year, 26-27, we are going to start MTech program in that discipline. And of course, that program is, of course, led by Professor Sudhir Ranjan Jain. Let me tell about him to you. Have you heard of National Quantum Mission? Have you heard of? So, National Quantum Mission, and for that you might have heard so much of 6,000, 9,000, 10,000 crores of rupees is assigned by Finance Ministry. And that National Quantum Mission document is prepared. And one of the core team member is Professor Jain. And he is there with us. Hence, we have thought of starting the MTech program in quantum computing from coming academic year. Already syllabus is prepared. It is approved in the Board of Studies, and it will be approved in Faculty and Academic Council and all the statutory bodies. It's not only starting MTech course, but creating a manpower, human resource in this field, not limited to 18-20 seats in the MTech, but across all disciplines in engineering college and various institutions. We float, quantum computing elective is there, honors course is there, minor course is there, and we have multidisciplinary minor course starting from this year. We are working so that, there are interested students should get benefit of this. We are planning to start one more course like nuclear energy engineering, which hardly any institute might have thought, starting such course. One more course like space science and technology. Already we have electives and honor courses, minor courses in the institution, but we aim to start this new courses. Who is going to start? Some or other institution has to come forward and start the courses. Then only we will be able to meet the requirement of industry. And that's what the thought process of management, and we are working on it. So, with this note about the university, about the Somaiya Vidyavihar, and about the school, and in brief about the courses, I stop here and see that, the participants from various institutions be there whole day and listen to the eminent speakers, eminent experts from this domain, which are sitting in the first and second row, which are invited by Professor Jain. And it's a very good opportunity for you people to listen to them and interact and talk to them during the break, and so that whatever this new technology, what we aim for, quantum computing. I remember one thing, when I'm doing my MTech or doing PhD, I used to visit IIT library and see the books, quantum physics, quantum mechanics, and some journals like, I was curious about that, what it is. I've not gone into details of it, but I'm always curious about it. And now we are talking about this quantum computing, and it's the beginning of that quantum computing era, I will say. Today we are talking about this artificial intelligence, AI era. But tomorrow it's going to be quantum computing. So we want to be a part of that mission, and we have started that mission with this program. So I wish each and everyone will be enjoying this whole day. Thank you very much.
I'm sorry to come back again, but I really failed in my address to express my gratitude to Professor Jens Koch. The screen is behind me, but I should not have forgotten. Jens is sitting there, close to midnight in Denver, an APS March meeting, and I asked him that, it will be late at night, you can just record the lecture, and said, no, I'll make sure to have a strong coffee and stay open. Thank you, Jens. Thank you very much.
Thank you so much, sir. Now I would like to invite our Vice Chancellor, Dr. Ajay Kapoor, to come and speak a few words.
Very good to see this august gathering of experts and our students also. Generally, when I sit here and think about what's going on, then a couple of thoughts are in my mind, and I'll do exactly follow the same pattern. And they generally go that, what is there for my students in this? We are organizing this event, what can they learn? And then what is there for our faculty here? And then that is purely with the purpose that young students, you are the ones who are going to build the new world. You are the ones who are going to run the society. So how this helps you? So let me come to that. So I won't preach you on what quantum is. I really know very little about it. And then experts are here, so I'll leave that for them. But you know that generally a couple of things have to come together. You have to go and maintain very, very, very low temperature. So engineering comes in. Then you have to understand physics very well so that you can understand all the states. And then very clever algorithms have to come together. So that in a general is how my mental model of this works. But then what does it do? And secondly, what can we do with that? It's a wonderful tool, we are told. I know it is. But then where can you use that tool? How can you use that tool, and what do you do? So let me give you my thoughts on that, and I'm pretty sure that we'll be told more about it. So we have seen last 50, 60, 70 years, the computing has worked very well for solving many problems. I'm still doing it. And we have artificial intelligence, which is also doing wonderful work. So why do we need quantum computing? What does it do? So you can tackle a lot more complex problems. So you go one step at a time, you go in parallel, but here you can really address things in a very, very different way. You can address very complex problems. But so what? Where can I use them? So if you see the world around you, most of the problems that we are facing are the ones that could not be solved. That is why we call them wicked problem. So you think about a person's life. You have to have some food. You have to have energy, light, AC in your house, transport running on that. You have to have some commercial activity and many more medicines. And you find that each of these are now getting very complex. These are getting very deep, very detailed. Using quantum computing, you can actually consider these complex problems. Now, if not now, in 5 years' time, 10 years' time, you will have incredible amount of power in your hand to tackle that complexity. Let me tell you, if you have 300 qubits, you have more states than all the atoms in this universe put together. So that is the power. You apply that to climate, you can understand it better. You apply it to soil sciences, you can understand that how soil is getting depleted, how can you rebuild it so that it starts to give better yield to the farmer, you can increase the quality of life of that farmer, that family very, very well. Medicine, discovering each molecule is now a couple of $2 billion, very expensive. Can you use this to develop those molecules, understand how they interact with the physiology, with the body? Take a step further, how they interact with an individual, and you can have individualized medicines. Consider energy. How do you tap into these unlimited sources of energy? How do you store? Can you design a better battery? Can you design a better solar panel? You have that power now. Even looking at the society, there's so much discord. People have their own way of thinking. How do you model 1 billion people? How they get influenced by social media? How they click a button? How do that affect the algorithm? You can tackle that. You can, with this technology that you will be working on, create a much, much better world that we have got today. So let me congratulate Dr. Jain for thinking of this, collecting such esteemed guests and putting them under one room, under one roof, and making them focus on a lot of very good issues. When he told me about it, I said that, look, ask everybody to tell something which is understandable by a layperson. And that was a request from my side, it still is. I want to understand what it is, but my faculty and students engage with this fully. I see that India's future lies in this. You remember last 25, 30 years, in software, India has done very well. India has got very natural strengths in maths, very natural strengths in physics, and engineering as well. So hardware side is one thing, but certainly the algorithm part is something India can do extremely well and help the world and help the society. With that, let me finish and congratulate everybody once again. Okay.
Thank you so much, sir. Now I would like to invite our esteemed chief guest, Dr. Sandeep P. Trivedi, to come and say a few words.
Thank you. Professor Ukarande, Professor Kapoor, Professor Jain, distinguished panelists, faculty members from Somaiya Vidya Vihar University, all the participants in this very exciting conclave, and especially all the students. It's absolutely wonderful to be here in your midst for such an exciting meeting. And I look forward to learning a lot as I go ahead from all the distinguished speakers and the conversations we have. So thank you so much, Sudhir, for putting this together and having me here. I won't take up much of your time because I do have a slot, right, of 20 minutes to speak. But I just want to say to you all, to the students especially, that is actually a very exciting time, and I hope to bring some of this out in my talk. It's in a very exciting time where developments from physics in quantum mechanics are now beginning to impact in a very big way, significant way, engineering, various aspects of engineering and so on, with the potential, we still have to see, but with a definite potential to really have transformative change in society. And so, it's a very exciting time. There's a very strong commitment on part of India in terms of the quantum mission, which Sudhir was involved in and which our dean spoke about. And so, there's both commitment from the government, commitment from the private sector. We might hear some of that today also, and actual exciting science and engineering to be done. So I hope you'll pay attention to what all of us oldies say. Don't go to sleep. And I hope you'll get excited because, of course, in the end, the whole purpose of this meeting is to get the young people fired up and think about working and learning more about this subject. Okay, so look forward to talking with you all the rest of the day. Thank you.
Thank you so much. Now we will proceed towards our speaker session.
So we have Mr. Jen Scott he's a professor at Northwestern University, USA. His works, sorry. So we have Mr. Jen Scott, professor at Northwestern University, USA. His work centers around improving hardware for quantum computing and quantum simulations. He holds several leadership positions, chair US Department of Energy Committee, creating roadmap of quantum information science applications, deputy director SQMS, Fermilab, USA, and so on. Now, I would like to invite Professor Sandeep P. Trivedi. He is a professor at TIFR, former director, TIFR. His specializations are, he is a theoretical physicist, one of the world authorities on string theory, quantum gravity, and quantum information theory in black hole physics. Now, I would like to request Professor Umakant D. Rapol to come on the dais. He is a professor at IISER Pune. He is a well-known atomic physicist. He has contributed significantly to the National Quantum Mission. At his lab, they have about 25 qubits based on ion traps. Now, I would like to request upon Professor Benoit Gremont to come upon the dais. He is a director of research at CNRS, France. He is head at nanophysics group at Marseille University, France. His interest lies in cold atom physics, quantum optics, and non-equilibrium phenomena. Now, I would like to request upon Professor M.S. Santhanam. He is a professor at IISER Pune. His interest lies in nonlinear dynamics and quantum chaos, quantum computing, and complex systems. Now, I would like to request upon Professor Manoj Nambiar. He is a chief scientist at TCS Research. His work focuses on classical computing hardware design and quantum computing. Now, I would like to start the panel discussion. Thank you.
Hello. So our plan of the event is to have an initial introductory discussion here with Jens Koch online. And so we're going to spend something like half an hour. I'm going to ask each of you a certain question, try to put them in the spot, initiate a discussion. And I have this pleasant duty to start with Jens Koch. So who is going, now, Professor Jens Koch is, of course, one of the authorities on how one does quantum computing using superconducting qubits. Jens, you have been in the epicenter of quantum computing based on superconducting qubits. How would you like the audience to adapt from answers only as yes, no, to an answer that appears as a superposition or a probability distribution? How is the audience going to build an intuition for such a thing that, the answer is not yes or no, but there is a whole set of answers which are possible, and all of that is possible?
I think the goal must be that in the end we're all entangled, right? But so I think you're mentioning something that has been on my mind for a bit, in particular in how we talk to the public about quantum mechanics. And I think we've told the story for a long time that quantum mechanics is just pure weird and strange. And I wonder sometimes, when I talk to my parents, I sometimes get the feeling that is actually off-putting. And so I try to tell the story more from the perspective of our human experience, of course, is limited in terms of what we can perceive directly. And that certainly goes for the small things in life. We cannot see individual electrons, for instance. And so the expectation that everything that goes on in quantum mechanics should just come natural to us is maybe expecting a little bit too much. But especially to those students in the room, I guarantee you that weirdness that some people warn you about, that will go away, and you will feel comfortable with quantum mechanics, and you will know how to predict things.
So, well, fantastic, very nice, very interesting way to begin this conversation. One more little thing is that when quantum mechanics came, one of the first things which was surprising was the aspect of microscopic tunneling. That, of course, we throw a ball at the wall and the ball is going to return, we are for sure, right? But now there was a possibility that a nucleus decays, and that decay process takes place by way of tunneling started by the great physics scientist George Gamow. From those microscopic tunneling days, we went to macroscopic tunneling. I'm reminded of what my wife says when the children are far away in their hostels, and they say that, Kuch Khan, we are not getting anything to eat. And she says, how nice would it be that if I prepare something and somehow it appears on the other end? So that doesn't work still. Although macroscopic tunneling, we had a Nobel Prize this year. So it's very important. Michel Devoré, John Clark, and Martinez, this classic work from 1928, microscopic tunneling, to 1962, Brian Josephson, macroscopic tunneling, to macroscopic tunneling's application giving rise to resonant activation of superconducting junctions in a circuit, the work of Michel Devoré, John Clark, and Martinez, to now, to qubits. Jens, what do you think? What is the next breakthrough of this magnitude?
Wow, you're asking fantastic questions.
That's easy.
That's easy. Yeah. So I would say that the small breakthroughs that are sort of baked into various roadmaps, quote unquote, those are relatively clear. We have to, in various architectures, not just superconducting qubits, we have to make sure that our individual building blocks, the qubits, the quantum bits, are sufficiently high quality so that quantum error correction actually helps us rather than making things worse. But if you're asking for things that will lead to future Nobel Prizes, I'm just as curious as many other people I think are, and I look forward to that.
Thank you very much. I had to put you on the spot, right, anyway, so. Okay, thank you. Let me go to Sandeep Trivedi. Sandeep is my dear old friend, so I can ask all kinds of questions. First off, Sandeep, we have this idea of quantum computing, okay, we understand that. We have classical computing, so we have quantum computing. So somehow we are going to do something faster and succeed, right? But then there is this thing about quantum information. Now, information, all of us have some notion of information, classical notion of information. Scientifically, Claude Shannon made this pioneering work which appears as mathematical theory of communication in the book and papers by Claude Shannon. Now, using that classical information, we have gone so far in building machines, communication, everything. I have to ask you, how would you like our audience to think of what to make out of quantum information, of trying to understand this old Shannon's thoughts in quantum mechanical setting? What do you think?
Yeah, well, I mean, that's a very good question. And I think as Jans was saying, the quantum world is different and quite different from the classical world around it. But that shouldn't put you off, because you can build an intuition for that world as you learn more about it, and then make predictions and use it for all kinds of technologies. But because the quantum world is different, the notion of information in quantum science is also different. And this is something which it took a little while, quite a while actually, many decades, for people to really fully understand that the inherent logic of quantum mechanics is different, and along with that, the notion of information is also different. And one way in which it's different, roughly speaking, I'll try to say a little more in my talk, is that quantum information is more spread out, okay, more distributed, because of what Jans again said, namely, the description of things get tied up together. If you have a system with different constituents, you can't just describe the system by telling what the different constituents are. But there's a notion or sense in which the whole setup is more tied together than its parts. Okay, and that means if you were to try and read a quantum book, just as an analogy, right? If you read a classical book, you start, okay, one day Sita got up and went to the forest. You're learning things bit by bit by bit, right? In a quantum book, typically, if you started reading it, this is an analogy, for about half the book, what you get is garbage, just nothing coming out. And then, as you read the rest of the half of the book, slowly information comes in. Okay, so this is because the information is so distributed that to begin with you don't see anything. That's a problem maybe, but it's also a virtue. And you can turn that into a virtue in many ways, for example, in how you send signals in cryptography and so on. And so the nature of quantum information is different, but it has potential that the classical world doesn't. Okay, long answer.
Beautiful, lovely. One small little question, right? Now, you and your community of theoretical physicists, and I also used to do theoretical physics, but anyway, you also worry about black holes and quantum gravity and so on. And there is this black holes is something that holds fascination of all present here, from science fiction to whatever stories. But you also have questions which are like information questions related to black holes, etc. Would you be able to say something if that can be understood? In what way should quantum information questions become interesting for black holes? Because we thought black holes is only something which is so strong gravity that light is not allowed and so on. Now, where is this information coming in that?
Yeah, that's also a very good question. So, of course, this question lies at the forefronts of, cutting-edge theoretical physics. So, just to take 2 minutes to set the stage, black holes are very interesting objects because they are as dense as anything can get in the universe, right? So dense that even light cannot escape classically, but in quantum mechanics, as Sunil was saying, things can tunnel out. Classically, you may not be able to penetrate the wall, but quantum mechanically, you can get past it, strangely but true. And similarly, light can tunnel out of a black hole, quantum mechanically. Now, Hawking, Stephen Hawking, the famous theoretical physicist, first showed that this could happen. But what seemed to come out was very kind of incoherent information, okay? Not containing any real knowledge of what the black hole is made up of, how it was produced in the first place, and so on. And so then people thought, oh, maybe in every other system, you don't lose any information, even in quantum mechanics. Maybe black holes are different. Well, if they're different, then does that change our fundamental understanding of the laws of nature when you apply them to gravity, et cetera, et cetera? And it's been a long course of theoretical development. And the verdict is not fully out. I'll say a bit more in my talk. But roughly speaking, what I believe, what many people working in the field believe, is that what Hawking, when he first thought he was getting no information out, was reading the first part of that quantum book I told you about, So he was just seeing no information. But if he had read long enough, or if we read long enough, then the information slowly comes back out. Okay, and
fantastic. So great. Wonderful. Now I have Benoit Gremont, again, one of my old friends, to bother him. Now, he has been interested in putting ideas of topology into quantum matter and things like that, which he's going to talk about. Topology, for everyone's understanding, you can't understand topology in a minute, but it's a branch of mathematics which is like rubber sheet geometry. So that's topology. Ideas from topology in condensed matter physics, the solid state physics generally called, were pioneered by David Thouless. He made tremendous contributions in that direction. Now, and David Thouless, one of the great thinkers in this direction. I have to ask Benoit, how would you go about explaining to our audience the basic idea of how a thing like topology, which is rubber sheet geometry, shapes of things which are equivalent in the sense that there is a medu vada with one hole and a cup with one handle are equivalent. I mean, now nobody in this world can imagine that medu vada and cup can be the same thing. But an idea like that can play a role in questions in quantum matter and eventually in computation. How would you go one stage to next stage, like topology and then matter, then computing? What do you say?
Sorry. It's a bit complicated, but I think that the main idea is that, the way I see topology, and it's not my idea, of course, many people have thought about that before me, I'm just recycling. So it's like knots, okay? So it means that in quantum mechanics, if you look at different properties, they can be classified when you have topology, because some situation you don't have. But when you have topology, essentially different system or different phase of the system, like water, ice, so you have the same situation for condensed matter, then they can, let's say, as if they were corresponding to different kind of nodes. And it means that you have a certain type of nodes. You cannot go to another type of node without doing something very hard to the system, so you have to cut something. And it means that the fact that you have these different kind of nodes for different type of your phase of your system is basically protecting your phase to changing spontaneously from one aspect to another. So this is how topology somehow is used in condensed matter, and that has been really like a tremendous way of understanding all this new phase of matter, and it has a lot of implication for, possibility in quantum computing, where precisely protecting information from any environment, temperature. If you could use topology to do that, then that will probably increase the power of our quantum computer, but it's hard to be used.
Okay, great, thank you. Very difficult subject, but I think you said very nicely. Now I have Umakant Rapol. Umakant is somebody who I have very special feeling. I've been the lab which had nothing at one time, and the Institute ICER Pune was in another campus, and so on. I've been associated with that institute for a very long time. And from that stage to build a whole lab and being a central figure in National Quantum Mission, Umakant has this distinction of making things from scratch. Umakant, you have to share with the audience, how do you manage to do this? What it takes to do this kind of challenging thing?
Well, I mean, ever since my PhD or even before that, I was used to building things from scratch. But after coming to ICER, I think it was, ICER offered a great opportunity to start such complex experiments in here. And one of our initial goals in the lab was to build an experimental system where you can produce what is called as a Bose-Einstein condensate. Now, many of you might have heard about Bose-Einstein statistics, which was initially developed in India by Professor S.N. Bose, and then later on Einstein took it further, and then they predicted that matter can enter into a very exotic state, which we now call as a Bose-Einstein condensate, where if you put particles like bosons, if you put them together, they can be put together in a container where all of them start behaving together like a giant matter. Okay, and if you look at the wave particle duality picture, then this entire set of these particles together behave like a giant matter wave. Now, that was one of my dreams, to set that up and then do some interesting physics with this matter. And now, going forward, I mean, there has been so much work with this matter which is created in the lab. Earlier, it was only known to be existing in exotic places like either in neutron stars or in liquid helium or so, but now you can actually create this matter in the lab. Now, of course, that itself was a great motivation to start such complex experiments, and it's not an easy task. It does take money, of course, but a lot of effort and a lot of highly motivated students who have been working in the lab, and yeah, that's how we started building this. And now we are in the phase where this knowledge is being extended towards making practical devices, as well as thinking about building quantum computers in India. Yeah.
It's fantastic. Now, just another question to you. I've been following what you have been achieving, year by year, and you had 8 qubits and single qubit gates first.
We are working on it.
Well, and then now there are going to be 2 qubit gates and more entanglement, something like 25 qubits, 2 to the power 25 possibilities to keep track of. So, what comes in the way of going from numbers like 25 to 1,000 qubits?
No, I think that depends on what kind of platform you're talking about.
Okay.
There are certain platforms where scaling is not a big problem, but at the cost of the quality of the qubits. There are some platforms like these ions, which are much more purer in terms of the quality of qubits, but there are hurdles to how many you can put them together on one chip. So it's always a trade-off. Right. Now, people are talking about platforms like single electron transistors, which probably you can make billion of them on a chip with the current technology. But then making the qubit itself is a challenge now. But if it can be made, then you can scale to billions of them, like using the existing semiconductor technology. The superconducting qubits, okay, I'm not an expert, but it has its own challenges. Probably Jens knows better. And there are these neutral atoms, which can also be scaled to thousands of them. But then again, there are different challenges. Now, it's not only about the number of qubits, because there are certain problems you can solve not in a way of what we think about as a universal computer. You can use them, okay, there are two ways I will talk about. I'll probably not get time to talk about it, but there are two ways to do quantum computing. One is analog quantum computing and another is digital quantum computing. Digital quantum computing is similar to our processors where you execute a set of gates. You make an algorithm, you make a quantum circuit in this case. You basically break it down to different kinds of basic logical gates, the way we do it in classical computers, and then you churn your problem, you run your problem through it. The other thing is it's more like going by the ideas that Feynman himself gave. You use a natural system to simulate another natural system. So you use an equivalent quantum mechanical system to solve a real problem, like a molecule. So that is like an analog quantum computing, rather more like quantum simulators, where you may not need so many qubits. So, yeah.
Yeah. Great, thank you. Wonderful. Now I turn to Professor M.S. Santhanam. M.S. Santhanam has worked on many subjects which can be summarized as science of complex systems, classically, quantum mechanically, and so on. And I would like him to explain to our audience that as we begin to learn and predict complex systems, we have used machine learning methods and new quantum machine learning methods and so on. So in going from machine learning to quantum machine learning, in making that shift, what is the demand on the mindset shift as you make your algorithm quantum and not classical? How is the learning experience to be understood and grasped?
I think the main shift in mindset, right? I think we need patience. It looks like a long haul. So I think that is what is needed first. But more seriously, I think what we are looking for is most of our data is essentially in classical form. Like you have maybe recorded either in written form or maybe in finally ASCII numbers and so on. So if you want to use any quantum machine learning technique, the numbers first have to be converted into quantum states. So one part of the problem is encoding. And then, of course, there is the core quantum machine learning algorithms, which will do some transformation on the data. And again, they being quantum algorithms will give you an output in terms of quantum states. So once again, for us to again make sense of it, we need to once again decode and bring it back into standard numbers. So I think if we are going to make any real use of quantum machine learning algorithms, we need to also work on these encoding and decoding techniques. Currently, a lot of, in fact, this is something that I'll point out later in my talk as well, that a lot of algorithms do exist which promise very good speed up, exponential speed up on paper, which don't take into consideration these, let's say, data loading complexities and so on. So I think a lot of work needs to be done in those parts as well, so that we can account for the true complexity of the end-to-end algorithm between taking the classical data and finally getting the classical output. Yeah.
So if I understand that all the mathematics, number theory, and all aspects of mathematics which go into encoding, encryption, and decoding, all those have to have to play a main role in as we march towards quantum computing, right?
Yeah, in a sense, yes. Because I think currently the kind of viewpoint is that somehow you can do that encoding in kind of order n complexity. So you assume that someone will do it for you and go ahead with the core part of the algorithm. But actually implementing it in practice, like if you maybe tell my colleague Umakant that now load this classical data into your ion traps, that is going to be far challenging. It's not going to work out in linear time complexity. So that is where I think the major challenge is. It's one thing to write mathematics algorithms on paper, another thing to actually get it to work and give you output.
So that tells
So there
us
is a gap there that
yeah,
needs.
that tells us the direction on which we all need to work, and at the level of curriculum to everything in our teaching, etc. We have Manoj Nambiar from Tata Consultancy Services. He's chief scientist, etc. So he has been in this high performance computing for a very long time. And so Manoj, I have to request you to explain to our audience how do you compare your days with your high performance classical computing and to high performance now maybe quantum computing? Are we gaining something, or are we just saying a lot of things? And in what major directions we would have to train our students, train the society? What are your thoughts?
Right, thanks. So high performance computing, I would say it's still there. I mean, we are not going to get rid of it any soon. And of course, we start from, looking at the use cases. Although when we learn, we start learning algorithms without knowing what they're used for, right? And slowly, when you start seeing the world, you realize how things fit in together. And you are able to appreciate the need for, what does it mean to look or design a car before it's actually manufactured? Or what does it mean to design a drug, without having to go through a lot of these wet lab tests and so on and so forth. So you start appreciating, starting from the use cases, and then you realize that, okay, you're able to appreciate the mathematics that come between, that is able to express these things very well. And it's not just the mathematics, you need the algorithms that will, put this mathematics into place. And of course, you need the compute and networking power, which will finally bring everything together and help you see the world for what it's going to be before you actually do it. And this is what has been shaping the industry forward in many ways. Talk about not just scientific and engineering industry, but even the finance industry, so to say. And there is no end to how people have creatively used computing to find a solution to their problems. And it's very difficult to comprehend them all. Now, coming to quantum, yes, there is a promise, right? I mean, talking about certain kinds of Professor Ajay Kapoor spoke about some complex problems which can be dealt with using quantum computing. And that is where the excitement is with quantum, because what you get with quantum computing today is a promise. And with that promise, there is hope and something to look forward to, right? We may be nowhere there today in terms of hardware, but nevertheless, we are not in a way to say that, okay, nothing's going to happen, even from an industry standpoint, right? I mean, of course, today the industry can make no big use of the hardware that is available, but we are not the ones to shut down and say nothing is going to happen. We keep searching for methods. We keep searching for methods in trying to weigh what can be closest to practical, if not practical. And from there, keep pushing boundaries. Okay, we cannot actually solve the problem of making it practical, but at least in my group, we've been trying to push, apply various use cases, see what it means. Because if I have a customer coming and telling me, is it going to make a difference to me? What we do is we take that problem, we try to encode it into a quantum machine, and we can speak to them in their language as to what it means if we use a quantum computer, where we are. And where we would like to get there is to say that you need so many resources to actually make reasonable sense of buying a quantum computer or even using a quantum computing infrastructure in the first place. So that's where it is. So prospects are exciting, and we are looking forward to making good use of these machines as they evolve.
Thank you very much. So we had this one round of introductory discussion. We'll conclude this here, and then this will be followed by presentations which are short, like 20 to 25 minutes, and we'll begin with Professor Jens Koch. We'll all go down, and this whole act of putting quantum thought together and making progress, creating new ideas in this direction is challenging. And I'm reminded of a quote by Claude Debussy, which says that works of art make rules. Rules do not make works of art. So we are in the process of this artistic work which will define the rules of the game and not the other way around. With those thoughts, I request panelists to please take the chair, and we begin with discussions. After each of these presentations, we are going to have interaction, so our panelists and everyone can add and ask questions. Thank you very much for your patience for this first session.
Now we are starting with Professor Jens Koch with the title of the talk, Quantum Computing with Superconducting Qubits.
Thank you. I would have loved to share my screen, but it says sharing is not turned on. Am I allowed to show slides? Send the request. Let's see. Yes. No, thank you. So I'll share my screen, get the slides up. All right. I'll hide the meeting controls here, which I think you can see. Okay, great. And so I hope that the audio is okay. I cannot see anybody in the room at this point, but I suspect that if things were not working, you would give me a sign somehow. So really, what a joy and honor to join you for this quantum dialogue. Thank you for having me. I apologize that I failed to visit in person this time. It looks lovely where you are. I hope that I might get the opportunity in the future. And I'll use the next 20 minutes to tell you a little bit about quantum computing with superconducting qubits. That's a topic that I got to participate in, and I got started actually as a postdoc when I joined Steve Gervin's lab at Yale almost 20 years ago. And since then, a lot has happened in this field. But some things, the motivation for quantum computing is still roughly the same. And there's one paradigmatic example which I would like to give, especially to those of you who are beginners in the room and don't know that much about quantum computing yet. Now let's see whether I can forward my slides here. Yes. So the simple example is one of a computational task that it initially may not seem particularly exciting. It's the task of factorizing integer numbers into their prime factors. And so for 15, I can do this in my head. For the next number, I'll struggle a little bit, but I hope that I'll succeed. But if I give you a number that has 400 digits, even you will probably struggle to find out which two prime factors I actually multiply to obtain this 400-digit integer. This asymmetry between multiplying integers is simple, but finding the prime factors is hard, is also behind certain encryption mechanisms. And so if you wanted to solve that task or decrypt something by brute force, you really face an uphill battle. This view graph here is a little bit outdated now. It's a rough estimate from 2005 now. So probably as far as classical PCs are concerned, things have sped up a little bit. But what this graph is just simply trying to say is that this computational task of finding the prime factors of a large integer number takes our classical computers, at least so we think. We don't know of a better algorithm than the classical number sieve, more or less. It takes classical PCs a very long time to accomplish that task. So if you had a number that is worth 1,024 bits, then your cluster of 100 PCs in 2005 was predicted to take 1 million years to solve this problem. And if you had a quantum computer that operated with a frequency of a megahertz, then you might be able to solve that problem within a day. And so that's impressive. I should point out that not all computational tasks are like this. At least we don't believe that quantum computers are just better at everything. But there are certain select tasks that are valuable to us, where quantum computers are either known or believed to be quite a bit more efficient than our regular classical computers. And so how is that possible? Our regular computers, everybody knows, work with bits. That they're the smallest unit of information. They're 0, 1. It could be a voltage that is high or low, a current that is on or off. And when we turn to quantum mechanics, something interesting happens where the quantum analog of a bit, a quantum bit, a short qubit, also has these two states, 0 and 1. But then quantum mechanics allows us to form so-called superpositions. So a quantum system doesn't have to be either in state 0 or 1. It can be in both at the same time. And in fact, there's a whole continuum of such states which can be represented as points on the surface of a sphere, the so-called Bloch sphere. So a qubit, if you want, actually has an infinite number of states. There's a caveat though. Once you want to get information out from this qubit, once you perform a measurement and you ask, well, what are you? The qubit will respond, if you perform the measurement correctly, with either 0 or 1 and nothing in between. And so that is already a hint that making quantum algorithms is not completely trivial, because in the end you will have to get classical information out. And so all this magic of the quantum world has to go bye-bye at that point. Now, how would you operate qubits? The simple picture, independent of what kind of qubit you have, is operations of qubits are rotations on this Bloch sphere. So you might take the system from the 0 state, which corresponds to the North Pole, to the 1 state, which is the South Pole. That's a so-called pi pulse. And there are other kinds of rotation. Here's a different example of the Hadamard gate. And so you put this together, not just for single qubits, but for multiple qubits. And if you build a machine that can perform these operations with sufficiently high accuracy, you have something that can carry out quantum algorithms. Okay, now I need to go forward. I'm going backwards, which is very interesting. Sorry. Here we go. All right, so the quantum bit that I already mentioned, you will hear multiple talks today in this quantum dialogue. And if you will, you could say there's a competition going on about hardware platforms. I would say it's a wonderful active field where we don't know yet which architecture is actually going to win. The fact that I'm sitting here and talking about superconducting qubits is more or less a coincidence. I joined Steve's lab. Steve was interested in superconducting qubits, but there are many other architectures around where people use trapped ions, neutral atoms, electrons, and quantum dots, photons. We'll hear about anyons and topology, all interesting ways of trying to pursue this goal of building a quantum computer. And we heard briefly already that indeed the 2025 Nobel Prize is one that celebrates a little bit about the superconducting qubit architecture. So John Clark, John Martinez, and Michel Devoret received this award for the discovery of macroscopic quantum tunneling and the energy quantization in an electric circuit. And it's exactly this last part that is so heavily used in superconducting qubits. So how do we think about superconducting qubits? The starting point is really very simple, and many of you, if not all, have seen an LC oscillator before. It's just an inductor coupled with a capacitor into a simple circuit. And so the idea is, instead of building this out of regular little circuit elements that are normal conducting, experimentalists know how to pattern such a circuit on a chip. They use some insulating substrate like sapphire or silicon, and then there's superconducting metal that gets patterned on top, or rather the metal becomes superconducting once this chip gets cooled down to dilution refrigerator temperatures. And once it is cold, some of the classical physics, of course, we can still discuss as you're used to it. So this chip, if you wondered what was the capacitor, it's basically this. You see, I've shown some electric field lines between the two plates on the chip. So once you charge the capacitor, there's an electric field. Once the capacitor discharges, there's a current that flows, and that current actually produces a magnetic field or a flux through inside your inductor. And so on the classical side, this is all very old and comfortable physics, if you will. I won't even talk about the equations that I'm writing down there because you've seen them all before. I'll maybe just mention that in our field, the kind of variable that we like to and end up using a lot is actually a magnetic flux or generalized flux variable. So this capital phi you can for now picture as the magnetic field that is built up in the inductor. And so once you turn to the side of quantum mechanics, this Hamiltonian, which is composed of a simple charging energy and the inductive energy, really looks like a harmonic oscillator with an equidistant energy spectrum. So the operators phi, or the quantities variable and conjugate momentum phi and q, turn into non-commuting operators, if that means something to you. If not, quantum mechanics will become your friend eventually. This is not difficult. And so this physics leads us with a system where these energy levels are equally spaced. And for operations of a qubit, that's not very convenient. So what we typically do is we actually employ microwaves in the gigahertz range to induce transitions between these energy levels. So to lift, say, the system from the ground state into an excited state. But since all these energy levels, again, are equally spaced, the bridge to the next higher level is equally large. And so you will just climb the ladder when you feed in microwaves and build up a coherent tone where multiple levels are now occupied, and that doesn't look like a good qubit. So we would prefer to keep the lowest two levels occupied, but nothing else. And so we would like to change the energy splitting in this harmonic oscillator a little bit. And that is done by substituting the inductor with a Josephson junction. Now, in these 25 minutes, explaining Josephson effect to you would be fun, but I would lose too much time. And so for now, I'll just say that this quadratic potential that we all love so much for the harmonic oscillator is simply replaced by cosine potential. That's what the Josephson junction gives us. And you see in the view graph on the right that indeed that means that the potential widens relative to the parabola, and that in turn implies that the energy levels become more densely spaced as you climb the ladder, at least for a while. There's more levels even above the top of the cosine potential. But since the energy splittings are now not equidistant anymore, we can play this trick with microwaves and actually to quite good accuracy leave the state inside the subspace of the lowest two levels, 0 and 1. And so this actually works pretty well as a qubit. And this so-called transmon qubit has been around for a while now. and is used in many places that pursue superconducting qubit technology for quantum computing. All right, I'll mention sort of one quick thing in a bit of self-advertisement, but also in the hope that some students might actually be interested. So my group a few years ago published an open source Python package, and it's really nice also for beginners because it has a little graphical user interface which you see displayed on the right. You can bring this up in a Jupyter notebook, and you can play around with different kinds of qubits. The one that is displayed right now is actually not a transpond qubit, it's a fluxonium qubit. But it's very easy to play with parameters and get an idea of what do energy spectra and wave functions, matrix elements, and such look like for these devices. All right, but I want to say a few words about what are the challenges in the field. That's important, especially if you're interested in joining this field. And so one challenge is we need to get our qubits past a certain threshold as far as performance is concerned, or sort of the accuracy with which these qubits do what we want them to do. All of our qubits are exposed to error channels. That's maybe with some slight exceptions for topological qubits. All qubits have to struggle with errors. And those errors tend to be a little bit more complicated and difficult than in classical computers, where for a classical bit, the basically only error that can occur is a bit flip. Right? If you wanted a 0 and you get a 1 instead, that's a bit flip. For qubits, where you saw that all the states that are represented on the surface of the Blocksphere are allowed, there are many more different kinds of errors that can take place. So you can have coherent errors where perhaps in every gate you actually slightly over or under rotate, and that can lead to errors. And then there are other types of errors that are more caused by the fact that the qubit couples to other stuff in the environment. You're not the only person the qubit talks to, and the environment in many ways we wish we understood better. There are lots of kinds of noises which we've given names in the past, but the microscopic origin of them is not particularly well understood in most cases. So there's one over charge noise, flux noise, all kinds of stuff. And the fact is that these error channels are detrimental to the quantum computer, right? So if you accumulate errors, eventually your whole computation is just going to be useless, and we need to work against that. Now, there's a brilliant and beautiful idea which basically goes back to the 90s, probably. Beautiful work that is I think as important as the first quantum algorithms, and in some ways really interesting that introducing redundancy among qubits can help us do this task. It's not entirely trivial, and if you've ever heard of the no cloning theorem in quantum mechanics, you might actually wonder how can this ever work? But in short, it does work. So there's again this idea, instead of encoding your quantum information inside a single physical qubit, you'll use maybe 3, maybe you use 7, maybe you use a whole bunch of physical qubits that all together encode one logical qubit. And then you'll perform little little measurements, if you will, that will tell you not exactly what the state of the quantum computer is. That would be bad. That might destroy the computation altogether. But those measurements are just going to reveal whether a certain type of error that you can correct has occurred. And if you find out that it has occurred, you will correct it, but not learn otherwise what has happened in the computation. And for that to really work and make everything better, we need our qubits to have sufficiently high quality, or in slightly more technical terms, our gate fidelities, which is basically a number that tells us how accurately do we perform the single and 2 qubit gates that we need to perform. Our qubits have to be above a certain threshold for that fidelity. And that's not very hard to imagine if you just had a whole set of very low quality qubits, that wouldn't help you do quantum error correction. So it's quite plausible that qubits have to meet a certain threshold. Unfortunately, the threshold is relatively high. And so everybody is working very hard to understand and mitigate error channels, make qubits give qubits higher so-called T1 and T2 times, which then really mean higher fidelities for gates. We now, well, we've seen the first few experiments. One beautiful experiment from Michel Devore's group, indeed, where they show that they can get to a point where employing quantum error correction just barely makes things better now rather than worse. So we're right around that threshold with some of our qubits, but there's definitely more work to be done. Now, sort of looking of what have we actually achieved, it's nice to flash here the first experiment, one of the really first experiments with superconducting qubits. This one was by Yasunori Nakamura and colleagues in Japan, back then at NEC Labs. And they showed a circuit which was called the Cooper pair box, actually very similar to the transmon qubit used these days, just a slightly different parameter regime. This first Cooper pair box had a coherence time of just a few nanoseconds. So that's the time for which the qubit remains properly quantum mechanical. And so a few nanoseconds is really not enough to do anything useful with a qubit like that. That's, you know, it might even take you longer to do readout and find out what the state of the qubit is. And by then it has already lost its quantumness. So that was a challenge, but we're now in a place in, well, this is a photo from 2023, that's a chip that IBM made. And you see from the print on the chip that they managed to fabricate something that has over 1,000 qubits. They're not error corrected yet. They probably all have coherence time somewhere in the tens to hundreds of microseconds. So coherence times have increased dramatically over the course of the decades. But we're still not in a place where quantum error correction is built into these chips. And that is really something that needs to be achieved next. The other thing that we heard already on the panel and several places, I think, is scaling up is what we want to do. So it's not just about quality of qubits. Of course, we also need enough qubits so that we can do useful things. And so when I say scaling up, the truth is that making copies of circuits is easy. That is certainly true for semiconducting circuits, where there's an entire industry that has perfected that. But it's also true for superconducting qubits. It's nano fabrication, and so making copies of circuits is really simple. But the challenge is to maintain high qubit performance as you do that. And there's a number of things that come into play that are interfering with that and making this challenging. I'll go through this list and explain those keywords a little bit. So we saw that frequency selectivity was important for performing qubit gates, right? We saw that if I wasn't careful with frequency selectivity, I would just climb up the ladder higher. Frequency selectivity plays also a role in if I want to talk with qubit 1 but not with qubit 2, I'll make sure that qubit 1 has a different frequency than qubit 2, and I'll use microwaves that are good for qubit 1 but not for qubit 2. Now, if you put 100, 1,000, 100,000, or 1,000,000 qubits on a chip, eventually we'll run out of frequency space, and so there's lots of ideas now of how to perform, how to put chips in a modular way, so that I don't have to even attempt to do frequency distinction amongst a million qubits, which would be absolutely impossible. And so this concept of modularity is really important. Certainly also for putting together chips of larger numbers of qubits, where we're still facing the fact that on the chips that get fabricated, there's always a chance that one of the qubits is actually not functional. And in the literature, there are actually examples of that. I think the Google quantum advantage experiment was of that sort, where one of the qubits that they initially had wanted to play with was actually broken, and that has to be dealt with. As we increase numbers of qubits, there's also more control crosstalk. So there are places where we feed in microwaves. There are places where we also feed in currents to control fluxes and tune qubit frequencies up and down. But as we do that in a space that gets more and more crowded with qubits, it's pretty clear that we need good methods and probably ultimately automated methods for mitigating and identifying crosstalk and then compensating for that. One thing that's particularly unfortunate about superconducting qubits compared to atoms is that, well, superconducting qubits are not atoms, in the sense that if you want to build multiple superconducting qubits and make them identical, you will never get two identical superconducting qubits, right? Two atoms, yes, they might be the same, that they better be. But for superconducting qubits, you don't get that luxury. And so there are uncertainties and parameters that come out of fabrication. What's perhaps worse is that we also observe that some of the things that get built actually then have temporal fluctuations. So if you, for instance, look at IBM's chips and how they operate their superconducting qubits, then they have to recalibrate these qubits over and over again, usually at least once a day. T1s and T2s can change over time. Qubits can drift in frequency. And so those are all things where some of my physics colleagues tell me, oh, Jens, you've stopped doing physics. You're now an engineer. And then the engineers tell me that, oh, no, you're still not an engineer. But it's an exciting field where I think quantum information science and engineering broadly, not just superconducting qubits, is a beautiful place where it's very multidisciplinary or interdisciplinary. You have lots of opportunities to have collaborations between experiment and theory, which is something I tremendously enjoy. You can talk across the boundary between science and engineering, which I think I do all the time. And if you're a student, I think it's also an interesting field because there's many career opportunities, not just in the US. There's I know less about the atmosphere in India and hope I will actually learn a lot more. I know that in Europe there's also a lot of activity. So I think this is a worldwide thing, and I hope that more people will be excited and join this field. And this, I think, brings me to the end. I'm also supposed to stop here, I think. Thank you for your attention, and I'd be very happy to answer questions.
Thank you so much, Jen sir, for your valuable knowledge and time. Now I would like to open the floor for audience queries, if any.
Hello, this is Bharti. You talked about that IM Condor, about roughly 1000 qubit processor chip. What is your thought of breaking RSA 1024, the algorithm which Shor's claim to break?
Okay, so you're actually talking about a direct application of Shor's algorithm, and so my understanding of that algorithm is that if you want to factorize say an integer worth 1024 bits, at some point you actually will need at least 1024 qubits to even just store which integer number you're attempting to factorize, right? And so my understanding is that to do Shor's algorithm, we'll need a lot more qubits. You will certainly, in the end, want that to be error corrected. I'm guessing that Shor's algorithm will still take us a little while. We heard that there are computational tasks sort of on the side of quantum simulation and analog quantum computing, which are much less benign and not as demanding in terms of qubit numbers. But I think Shor's algorithm is likely one where we need large numbers of qubits
Because
for it to be
the
really
world
interesting.
seems to be in panic and trying to migrate towards post-quantum cryptography for TLS and all. It depends on that RSA encryption.
I'm sorry, say again?
I am saying that world seems to be threatened and everybody is now migrating towards post-quantum cryptography for TLS and SSL just because of this.
Sure. I mean, I understand that there are places where having security is so important that nobody wants to bear the risk of, when is the first larger quantum computer going to appear, and is it going to be public or is it going to be secret, and who will crack my credit card data? Like, of course we want to be safe and people are careful. I would be very surprised if within the next 5 years a quantum computer would be ready to set a new record in cracking the factorization of large integer numbers. I think that'll probably take us a little bit longer still. But you're right, people are worried about that, and there's algorithms, classical algorithms in place for encryption that are not prone to being broken by a quantum computer.
Thank you.
So thank you so much for the talk. So my question is there any, because you said superconducting qubits have a few disadvantages. So can you create a hybrid architecture where you can mix superconducting qubits with, say, ion neutral atoms or something like that, and maybe make a system which is a bit more easier to handle or something? Is there progress in that field?
I think that's a brilliant idea. One thing that people are still working on, which will have to be put in place for your idea to bear fruits, is eventually we will have to be able to do transduction. We will have to be able to convert from microwave photons to optical photons in a coherent way. And doing that with high efficiency, I think, is still very challenging. And that would be, once that is in place, I think the idea of having a hybrid system with different types of architectures providing qubits that are good at different things seems very strong and promising to me. But we'll need transduction, right?
Thank you so much, sir.
Sir, this is Rohit, and I am from biotechnology background, so I have some question regarding that. So you said that superconducting qubits are currently limited by decoherence. So I want to ask that in bioinformatics we need a large number of qubits to simulate a single compound or an enzyme. So does the future lie in transmon arrays, bigger transmon arrays? Or must we move to inherently noise protected circuits like 0 pi qubit to reach biological relevance?
I would love to understand a bit more what you have in mind with doing with qubits in this context, so that I understand what the requirement is. Can you elaborate a little bit more?
In bioinformatics, when we simulate a enzyme or a compound, it's required a large number of logical qubits. So I am just asking, to reach a biological relevance, so are we looking toward transmon arrays or noise protected qubits? in the future?
Yeah, so the noise protected superconducting qubits, you mentioned 0 pi, that's one of the flavors. There's nothing in place currently that I would say looks like it's easy. 0 pi actually looks more difficult than we thought in the beginning. Any noise protection that you can successfully build into your qubit is going to be helpful. Yes. But I do think that in the end, for an application where, and it sounds like maybe what you're suggesting is really sort of a digital simulation of the, like, solving the Schrödinger equation, for instance, on a digital quantum computer, right? That might be a thing that would be interesting, but I really think quantum error correction will have to be in place for that to be useful. Or I need to understand why your system accepts a lot more errors and noise than I currently think.
Hello. Nice to hear you. Great talk. So I have a question regarding the fidelity threshold things you are playing around with. So when we moved from the parabolic potential to the cosine potential, so you're basically separating the energy levels, right? And we want to separate the levels to a larger magnitude, if I understand correctly. So as we know, like, the quantum systems are always susceptible to tunneling. So how does that play a role? Like, even if you move from a cosine potential to move towards a cosine potential, the kind of stability you can achieve just by changing the form of the potential, and how does that work together with the tunneling effects which quantum systems are always susceptible to? Can you throw some light on that? Thank you.
Yeah. So for the transmon, for the cosine potential that I brought back on the screen, there is actually an effect of tunneling, but for the transmon, it's very weak. You see this fictitious particle that lives in this cosine potential, if you will, basically lives on a circle where phi equals 0 and phi equals 2 pi are basically the same configuration. Now you can tunnel from that minimum into that same minimum across the cosine peak, if you will, and that is an effect that is important. But it's important in a different parameter regime. So in the Cooper pair box, it's very important. And charge noise and the effect of this so-called offset charge, which I didn't mention in my talk here. Tunneling is really important for that. In the transmon, that sensitivity to charge noise of the low-lying energy levels is much reduced, right? Because now these energy levels are localized, they're deep inside the well, and tunneling is actually very strongly suppressed. Does that answer your question?
Thank you very much. Yeah, thank you.
Okay.
Hello. Sir, I have one question regarding going from 1 qubit to n qubits. So what is the challenge? Is it like a dimension on which we put the qubits, or the interaction between the qubits so that they all can go in superposition at one time?
Yeah, so placing multiple qubits on a chip is easily done, but then the question indeed becomes, what is the interaction between the qubits, and is that interaction tunable, right? Because for 2-qubit gates, where I perform an operation on qubit A, depending on what the state of qubit B might be, that only works if there's controlled interaction between the qubits. And so if you just loosely place qubits in an array, they will probably, especially transmons, they will all just capacitively couple, and that's an interaction that you cannot turn off. So oftentimes what people do is they place transmons they use couplers in between transponds. That's one scheme. You can also intersperse transponds with sort of separate them on different ends inside a microwave resonator. But it's very important how they are arranged, how they're physically coupled, whether that coupling is tunable, to what degree you can really switch it off, so that this interaction is not active all the time. Those are all important aspects. Yeah.
Thank you, sir.
So thank you so much, Jen Scott, for the valuable knowledge and the information you shared. So now I would like to call upon Sandeep P. Trivedi for his title, for the talk, which is titled as the Quantum Frontier.
Interference while communication between the qubits, and do we have any mechanism to handle that?
Sorry, was this still a question for me?
My question is how we will handle if there is interference between communication between the qubits. Do we have any mechanism, or have we thought about this interference while the qubits are communicating?
So the operations on multiple qubits are that they're unitary operations, and if you will, interference you could say is part of that. But so we steer quantum information by means of these single and two qubit gates. That is how quantum information gets distributed and routed and steered. And beyond those unitary gates, and then sort of later on measurement, there's no separate communication, I would say.
Okay, thank you.
Thank you so much, Jen sir. Now I would like to request Sandeep sir to start with his speech.
Okay, well, good morning again, everybody. And I've got a very general, I think I'll walk around a little bit. Well, I got a very general talk, and I apologize to all the experts in the audience. Already the questions made me aware that you all know much more than I do, and much more than certainly I thought you would know. So I've got a very general talk here, and hopefully it's of interest at least for some of the students in the audience. Well, Jens, it was great to hear your talk, but I really think you should go to sleep now. And you're definitely not going to learn anything from mine. Okay, so my talk is entitled The Quantum Frontier, and it's a more general kind of talk. And what I want to discuss with you is this new frontier of what's being called the quantum frontier. And it's a frontier in our knowledge of both science and technology. Now you see, there are many frontiers in science, and you might have heard about some of them. There is the frontier which probes the very small, deep inside the atom. This is the field I worked in for most of my life. You know, at CERN, we have the world's finest microscope where we smash, two protons together to probe the smallest distances ever seen. That's a frontier, but I'm not going to talk about it. Then there is the frontier of the very large. You know, you go from galaxies to clusters of galaxies to the universe as a whole, 14 billion light years. That's a frontier. We're learning amazing things. The very small connects to the very large. I won't talk about it. Then there's the frontier of the very many new emergent phenomena that come about when you put simple constituents together, okay? This is the domain of material science, condensed matter physics, and if you put very many artificial neurons together, it's the domain of AI today, right? And what I will talk about does pertain to some aspects of material science and condensed matter physics and so on, but this is not directly my primary focus today. What it is a new kind of frontier, okay? And it pertains to a growing understanding of quantum mechanics, its true meaning, its true significance. And since quantum mechanics provides the bedrock of our understanding of science, okay, this is what I want to emphasize. Science, we've learned a great deal over the many centuries, but that understanding rests on this bedrock of quantum mechanics. And therefore, as our understanding of quantum mechanics is growing, okay, it promises to have important implications for vast areas of science because they rest on this understanding. Physics, chemistry, computer science, and several aspects of engineering, even mathematics. Okay, and I want to give you just a very broad view of that. Some of the topics have already come up, but just to kind of whet your appetite. So you can think of quantum in a sense as sitting as this very interesting intersection today of many different areas. And even if you're an engineer today, you know, quantum could be of interest to you. If you're a chemist or a physicist, certainly, and so on. Okay, now, I want to also convey the point which also came up, that I think there'll be a lot of exciting developments in the coming decades, and also it's an opportunity, especially in India, you know, to do something good. Because there's a feeling, which is of course correct, that we missed the bus when it came to semiconductors, right? We were not prepared, and we missed the whole bus. The entire semiconducting revolution went by us. We're only trying to play a catch-up game, but we can't miss the bus again, okay? And so there's a great deal of determination to try and make sure that we are participants from the beginning, and I'll come back to this at the very end. And so it's wonderful for students. There's funding, there's institutional commitments, and there's a real possibility of building a career. Okay, now it might seem strange, why is there this renewed interest in quantum mechanics? After all, quantum mechanics is about 100 years old, right? We just celebrated a few years ago the centenary of quantum mechanics. For young people, 100 years seems a long time. Not such a long time when you're my age, but anyway, okay? So why is there this renewed excitement? And the reason, as was said in the discussion, is that the quantum world is strange, okay? We don't want to overdo it, but it's true, it's strange. And it's strange because it's very different. The underlying intuition in the quantum world, which can be learned, is very different from the classical world, you know, in which we normally live, and from which our intuition and understanding naturally stems, okay? And this means it's taken about 100 years for people to, you know, truly begin to understand in a deep way the meaning of quantum mechanics and its potential and possibilities. Okay, here, I'll give you two quotations, then we'll go on. Here's Niels Bohr. Niels Bohr is one of the father figures, as you know, of quantum mechanics. But this is what he said in 52. This is many decades after quantum mechanics was formulated, right? And he says, for those who are not shocked when they first come across quantum theory, cannot possibly have understood it, okay? Because it is very different, very shocking, if you like, from our more classical way of thinking. And the second quotation is from one of my favorite figures with whom I started my graduate career, I have to say, and it's typically Feynman, and he says, I think I can safely say that nobody understands quantum mechanics. I don't understand it, I'm Richard Feynman, therefore, okay? But actually Feynman did remarkable work in trying to further our understanding of quantum mechanics, and especially for the topics of interest today. Okay, now two properties, this is the most important part of the talk. Two key properties make quantum mechanics very different from classical mechanics. And this is what makes quantum information and quantum systems very different from their classical counterparts. The first property goes by the name of superposition. And it has to do with the following. As you probably know, in the quantum world, you don't work with certainties, but with probabilities, right? You might have heard of the Heisenberg principle of uncertainty. But it's even stranger than that. Probabilities we can live with because we work with them in our day-to-day life, right? There was some probability that I might not have woken up in time today, causing my friend Sudhir to get really worried if I didn't show up, right? Okay, there's always some probability of things going wrong or right, etc. That we can live with. But the quantum world is stranger. The a priori concept in the quantum world is a probability amplitude, okay, out of which you build the probabilities in the quantum world. This amplitude is a little bit like a wave, okay? So think of it as a wave at every point. Let's say the amplitude to find a particle at any point, and you have to take its square, okay, absolute value square to get the probability. So it's not a concept we are familiar with, right, in our day-to-day life. You think of it like water waves. Okay, water waves which come from various places and interfere to give a net amplitude and which you then square to get a power, except here it's this very mysterious thing, the probability amplitude, which is interfering as things evolve, okay? So this is one reason that quantum mechanics is so different. You have this probability amplitude which comes in various directions, various ways, and interferes with each other. Okay. The other reason, I'll skip over the double slit and all, you all have seen it or should see it. By the way, Feynman Volume 3 is the volume for quantum mechanics, and read the first few chapters. If you're a student interested, I really, really recommend that presentation. It's hard to do better, even today. Okay, the second interesting concept and key concept is that of entanglement, which also came up in our discussion. And this is a much more subtle concept, okay, in a way. And this has to do with the fact that the description or information content of a quantum system with several constituents, as I was saying earlier, cannot be simply obtained from that of its individual units, okay? Instead, the information is kind of shared. A lot of the important information is shared, all tied up or entangled, as it were, among the constituents. And this property has no classical analog. And many of the reasons for being so excited about the quantum world, about this new frontier, stem from understanding entanglement better and trying to put it to use, okay? And just to tell you a little bit how it's different. See, if you're in classical mechanics, if you have a particle, right, everybody knows, okay, to describe the particle at any instant of time, you give its position and momentum, or position and velocity, right? Okay, if you had two particles, what would you do? Okay, well, you have the first particle, its position and momentum, second particle, its position and momentum. Keep track of all these four pieces of information and you describe the whole system, right? So the description is made out of the individual descriptions. Of course, these particles can interact with each other, there can be forces between them. That's fine, they will affect each other, but at any instant, if you're keeping track of the information in the system, it's just the sum of the two particles' positions and momenta, okay? But not in quantum mechanics. In quantum mechanics, it's not true that the wave function of the two particles, psi x1, x2, which is the full description, can be broken down into a description of just one particle and the other, okay? It's not as if, for example, psi x1, x2 is a product, typically, for most states, okay? And this fact, it's already blanked out, okay? This fact that, it's not just made out of individual descriptions, it's more entangled or tied up. This is a key property of quantum systems, okay? So this is really the main thing I wanted to tell you. These two properties of probability amplitudes which can superpose so that, sometimes what can happen in waves is you get destructive interference, right? Two individual waves have some amplitude. They come together at some place with the correct phase, and it's as if they cancel each other. When this happens for the probability amplitude, it's as if, the probabilities net have cancelled each other. This can't happen in the classical world, because probabilities can't get negative. So superposition and entanglement. Okay, now I'm going to very quickly end my talk. Just to say, I already said this, but just to say it again, this makes, for example, a classical book very different to read from a quantum book. When you read the quantum book, you don't learn anything for a while, then you start learning information. So it's very different, it's a very different concept of information, etc., etc. Okay. Very quickly, I'll just tell you, already discussed quantum computers. I won't go into it, except to say Shor's algorithm, everybody talked about it, except to say, okay, here, I do want to show this. Here's my colleague, R. Vijay Raghavan in TIFR, who's building India's first quantum computer based on transmons, the kind of technology Jens talked about earlier. And it's part of the National Quantum Mission, which many of the panelists here, Umakant, etc., Sudhir, have been instrumental in getting going. And it's an example of an effort. You'll see more in Umakant and so on's talk of the kind of commitment the country is putting in. Also, just to say, the structure of the National Quantum Mission, as you know, is a distributed one with hubs and spokes and so on. So universities and institutions of all kinds can get integrated together. Okay. But I do want to say one thing. There's a lot of excitement about quantum computing, but we have to recognize that there are lots of formidable challenges, okay, to build useful quantum computers. And so while we're excited, we also have to be a little cautious if we are going to go forward. I think we heard some of that caution in some of the panelists. Some of the other areas, for example, in cryptography and communication, in sensing and so on, might actually bear dividends with greater certainty, in my view. Okay, and some of that is already beginning to happen. And I'll give you a couple of examples of that. I think quantum matter we'll hear about anyway, so probably I can skip. But let me just say one small thing, which is, we've had this remarkable progress, right, in our understanding of materials and so on over the centuries. But from the perspective of today's physics, almost everything that has been learned, whether you're talking about metals, insulators, semiconductors, and so on, can be reduced essentially to understanding single particles, okay? For example, single particles or effectively single particles in metals accounts for their behavior. Similarly in semiconductors and so on. What people are now realizing is you can have new states of matter where many particles come together in an entangled way so that they cannot be described as if they were individual constituents, okay? Because that's what entanglement is. That gives rise to new phases of matter. Their properties are leading to a lot of excitement, okay? So I'm going to skip over that. I wanted to tell you about a theoretical aside, which was my work, about how do you make entanglement quantitatively precise. And this is kind of interesting. The theoretical structures which underlie much of physics have to do with interesting symmetries called gate symmetries, all kinds of subtleties in making entanglement, which is this quintessential quantum property precise. And we did work on that, but, let's move on just for a minute, right? No, Sudhir is pointing to me, but I think I'm running out of time. So let me just say a couple of words. Okay, if you take something, if you take electromagnetism, right, which is familiar to all of us, and you think about it quantum mechanically, it has many interesting features. For example, if you had the magnetic field, which is completely localized in some region, and you have electrons which don't go into that region at all, but go around that region, you can still tell the magnetic field contained in the region. This is a very old result by Aharonov and Bohm and so on, which has to do with the fact that you have the underlying description involves the wave function, and you can superpose different ways of going to a particular location, like waves come about. And this kind of behavior of electromagnetism then means when you try to think about how the description of different units or constituents gets tied together, it makes it rather subtle, because how they get tied together has to do with the paths they take to get to places and so on. And so there's all kinds of beautiful mathematics and subtleties, and it can all be unraveled, and you can give precise definitions. So there's very, very nice theoretical work to be done at the quantum frontier. There's also very nice theoretical work to be done in computer science, okay? So we talked about Shor's algorithm a lot today. Somebody talked about Grover's search algorithm. But I'll just take 2 minutes. But, there are very few algorithms known today, actually, where quantum systems provide a significant speed up, okay? This is something we have to recognize. It's a great area to work. In computer science, they have these complexity classes, Depending on how complicated tasks are, you can classify them. Can they be done polynomially in the size of the input? Can they be done not polynomially, but whether you got the right answer or not can be verified polynomially, etc., etc. Today we don't know, and many computer scientists will say it cannot be done. Anyway, we don't know whether quantum computers will be able to do tasks which are non-polynomial in the sense of being harder than polynomial to do and polynomial to verify, okay? And it's a very important question, okay? Can what are called NP-complete problems be solved by quantum algorithms, okay? So there's a lot of theoretical work to be done also in computer science if you want to take the ideas forward. Okay, last of all, black holes. I think I already told you about this, but I'll just tell you. Just to tell you the various uses quantum information is having. Okay, this will be fun. Do black holes follow the laws of quantum mechanics? Hawking said no in 1974 in a very famous paper which started a lot of people thinking that maybe you have to revise quantum mechanics. But in 2004, he changed his mind and he said yes. And the reason why he said yes was the work of this very brilliant young man. He was just got his PhD a couple of years before 2004, who wrote a paper suggesting that probably the answer would be that you don't have to revise quantum mechanics. And I'm simplifying a big story, but it has still taken time from 2004 to 2024 or so, 20 years more, before people are more and more convinced that, quantum mechanics is secure, even when you confront it with gravity. And what has played the key role in making people go from no to yes is entanglement, okay? And it's what I said to you earlier, that this book, when you read it, Hawking's calculation showed no information coming out, but today I should have had a graph. It's as if that calculation is only for some of the time. If you go long enough, the information starts coming back up. And showing that it comes out is more challenging, but that's the kind of calculation in toy systems people have been able to do. I'll quickly end. I want to give you an example of what can be done, when you get going, if you have an engineering background and so on. And so I was somehow called in to oversee a defense research development organization, young scientist laboratory on quantum stuff. And well, what do you do with a bunch of engineers? This might be fun to some of you who are trained as electrical engineers in this case and wanted to work on radar, but are told, work on quantum, right? So, well, what do you do? Well, we thought, okay, let's build a quantum random number generator because, people in electrical engineering know about communication and signal processing and so on. And so that's what we did. And in 2 or 3 years, they built a quantum random number generator, which is comparable to the best in the world, went through very severe certification. Before the armed services are going to incorporate anything for their communication, you can be sure they're going to test the hell out of it. There were 7 levels of certification that the Army Corps of Signals subjected this technology to, and it came through. It's as good as the best in the world, built in 3 years by engineers with no prior knowledge of quantum, okay, and now has been deployed actually for communication purposes. So I give this example if you're an engineering student to tell you there's a lot to do. And there's a lot to do here, it turned out, not only vis-a-vis the quantum technologies, but there's a lot of back-end electronics that has to be built, And that back-end electronics also is something which is new sometimes, hasn't been so far built, and is something that engineers can really contribute to. So, okay, lots of hope and lots of possibilities. So, to summarize, sorry for such a general talk, but I just want to convey the excitement to you all that the quantum frontier is really opening up in science and technology with great promise to change, many exciting possibilities for engineering too. And, here is the finance minister, as was referred to several years ago now, announcing the National Quantum Mission, and which has now gotten going. And so there's a great deal to do and a lot of commitment on all sides to do it. So I invite all the students to join in the fun and Somaya to join also in this effort. Thank you.
So if anyone has any queries, you can go.
You don't have to ask a question.
Hello, good afternoon, sir. So I just want to have like one small question. When we say quantum matter or quantum material, so which property we are like looking for? Like, thing.
Well, I mean, it's a general word, of course, to describe any material where you need quantum mechanics to understand its properties. So in that sense, it's a very general phrase. But in the context in which I was trying to use it today, when I say it connects to this new frontier, I mean materials where, let's say, the kind of special quantum properties involved in entanglement, etc., begin to play a role. These are still somewhat exotic materials compared to what we normally have. But they're increasingly being explored, and the entangled properties of these materials hold out the hope that we can do things with them that we might not have been able to do otherwise. For example, they might have excitations which you can use for quantum computing. I don't know, maybe we have a talk on that later. That's one example. Or maybe you use those excitations for other purposes and so on. So these new kinds of materials, which are not conventional quantum systems whose behavior has been well understood in terms of single particle states and so on, that's the kind of material I had in mind when I was referring to quantum.
Thank you, sir.
Okay.
So I would... So before I ask my question, as a first year here.
Oh, yeah, hi.
Yeah. Before I ask my question, as a first year student who does want to go into a theoretical field, I did appreciate the generality of your talk. But anyways, my question was, in the previous talk by Professor Jens, he said that in reference to decoherence, that a lot of noise can occur with qubits which we have to correct, and that we don't really know what a lot of these noise sources are. But in your talk, you mentioned that we are already in the process of making a quantum computer, or India's first quantum computer. So my question was that how are we able to consistently just ignore or protect qubits from these noises without knowing their sources, to the point that we're able to consistently make a computer?
Yeah. No, that's a great question. It was a key question when people started thinking about whether quantum computing would be possible. And interestingly, the idea is that you use entanglement, to beat these kind of noisy effects you're talking about. So the basic idea is this, in error correction, even in usual classical systems, is to use redundancy, to try and beat error. So for example, suppose I had one bit, right? And it was, you wanted it to be up, but some effect made it go down, right? That's noise, right? And that's an error. So how do you guard against it? Well, you reproduce the same information in 3 identical bits, each of which is up. Now, if the chances of a bit flip are low enough, okay, at any instant you use the democratic rule. That is, you look at all the bits. If the majority are up, you say, oh, the original bit should have been taken as up. Okay, because the chances of a flip are small enough. Okay, there's a version of this you do in the quantum world. It's more subtle because of what Yen said, which is you can't simply clone qubits, okay? But you can nevertheless prepare qubits, say 3 of them, in an entangled state, okay? So I don't know if you know about qubits, but qubits can also be in up and down states. That's different from the up and down for bits, but anyway. So you can take a state of 3 qubits, which is up, 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 plus down, 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 okay? And then, in this case, again, if you have a qubit flip as an error, you can use a similar kind of democracy rule to be able to correct for it. And so on. You know, that's not the only kind of error you can get in the quantum world, but you can correct for it. So the bottom line is, there's at least a good theoretical edifice which says, if the amount of error in storage, say of qubits, and in the gate operations, you know, which you would have to carry out, is below a certain tolerance, okay, then you can, by having enough redundancy, do reliable computing. Okay, but that's a theoretical result. A, can it be implemented experimentally? B, can it be implemented experimentally on scale? Because, you know, for example, even the simplest protocols require you to go from 1 qubit to 5 or something. But now you have to put in gate operations which you're protecting against and so on. So for every one logically secure qubit, you have to actually have a very large number of physical qubits, right? And if you want to implement the Shor algorithm on a number of any halfway decent size, you're going to need millions of qubits, physical qubits. So whether we can achieve this kind of scale, I don't know. Okay, now I don't know so much about topological computing. Maybe we'll hear about that. There the errors may be smaller and so on. That's one reason people are excited about. So maybe those platforms afford more hope. We'll hear about some of that. But generally speaking, this is the reason. You know, you can control errors if they're small enough, theoretically at least. Okay.
Thank you so much.
I have a question. Like,
go ahead.
You mentioned Aharonov-Bohm effect.
Yeah.
So, like, is that a consideration when we build quantum computers? Because we try to shield them from fields, but are we shielding from potential?
Something like the Aharonov-Bohm effect is actually used in terms of how you manipulate some of the qubit or effective qubits that you produce. Again, we might hear more about it, but you have these excitations, and when they go around each other, they acquire a phase, and that phase can be the consequence of the calculation or computation you want to do. Okay, so something like that is definitely used in some platforms, not in the Transmon platform that Jens talked about, but in some others, and it's tied to how you can use topological properties, you know, for computation. Because the Aharonov-Bohm effect, in a sense, you can say is a kind of topological property that you have a system with a hole in it. You're not directly able to probe the hole, but you know, you have some magnetic field threading that hole, and you're able to sense it without directly going into it. So it's tied to topology in space also. So in some cases, but not all platforms, you try to use those kinds of effects.
And one more question, we have so much noise because those qubits that we're using, they interact with the environment. So in future, can we expect to have qubits inherently like the ones which don't interact so much with environment? Like, can we expect probing in the same way as we probe the galaxies using neutrinos and stuff? Like, can we expect some kind of like building some system which...
Yeah, so I think some of there are people who are better qualified, but you're saying, can you just inherently use qubits which are less prone to interaction. And you do have the advantage depending on which platform you use. And others should say, but you want to make sure you can do two things. You can have qubits which are immune from being corrupted by the environment, yet which you can manipulate, right? And so there's a trade-off there, right? I mean, if it's too isolated, that's also not very good for us, right? And so it's, trying to balance those two requirements that requires, in general terms.
Thank you.
Okay, many questions, but how about the other speakers?
Hello sir, I am an 11th grader and I had a question regarding quantum entanglement.
Okay.
So my question was, can you explain quantum entanglement in terms of the research, recent research done in quantum teleportation?
Okay. Well, it's rather the other way around, that quantum teleportation is possible because of entanglement. Okay, so what is quantum teleportation? It's one of these mind-boggling things, okay? Yeah, wrap it up, Sudhir is saying. I'm going to close it. Teleportation is one of these mind-boggling things, okay? Here's what the protocol involves. If you look at a quantum system, right, you disturb it, okay? Now, if I gave you a particular qubit, okay, and I said, you're allowed to make a phone call, send classical bits to your friend who's somewhere else, in Calcutta, and convey to him, please, what is the state of this qubit, okay? So, it looks very hard. I mean, it's impossible because I don't know what the state of the qubit is myself. How on earth am I going to be able to tell him what it is, right? And I can't find out what the state is because if I look at it, I disturb the system. I'll get some answer, up or down, but that wasn't the state in general to begin with. Oh, it looks impossible. But if you and your friend in Calcutta shared an entangled, okay, qubit, that is, you had a qubit and your friend had a qubit and they were both entangled, maximally, whatever, entangled, then there is a way in which you could convey on the phone some information after doing some experiments to the qubit I hand you, and your friend would do some experiments on the qubit he has, which is entangled with your qubit, okay, and his qubit would turn into the one I handed you. Okay, now there are two, I would have to say it more correctly, but it's a mind-boggling thing, okay, made possible by entanglement. So actually, entanglement is the reason why you can do these very funny things. And just to tell you, this provides a mathematical way to make entanglement precise. That is, if I said to you, I have so much entanglement in a system which has two parts to it, okay, then what does it mean operationally? In physics, we always like to, what does the length mean? Take a ruler, so what's the operational meaning? The operational meaning is how many qubits could you teleport, okay? That's the operational meaning. And that's actually what we used when we had to define entanglement in much more situations where it's not clear to begin with. Okay, the long answer.
So is
I can
that
talk
how,
to you more later.
So is that how the information from, example, in atom in a box A was transferred to atom in a box B, like in quantum teleportation experiment?
You'd have to tell me more about what precise experiment you had in mind before I can answer that. But if teleportation was involved, then certainly entanglement would have to have been involved to make it possible. Okay, thank you.
Okay. Thank you so much, Professor Sandeep, for the valuable knowledge you shared.
Can I ask a question? Last question. Okay. You talked about quantum random number generation, right? Yeah. So can you explain how true randomness and pseudo randomness happens in quantum random generation?
Well, okay, let me at least try a little bit. So, I mean, the interesting thing about quantum mechanics is that it gives rise to true randomness, okay? It's a very interesting thing philosophically, Can you have true randomness? And in quantum mechanics, the answer is yes, you can. And So that's, the random number generator I told you about, it uses a childishly simple principle. You have a beam splitter. Just think about it as a mirror at 45 degrees. Your photons coming in, with probability half they go horizontally and probability half they go vertically. At root, of course, getting it to work properly is more complicated, but it's a very simple idea, right? And it's really true that it's mathematically, it's with strict probability half that you go one way or another. So you get a truly random, generation of a number here, like a truly random coin toss. Okay, now pseudo-randomness is a more complicated concept. And it has to do with something which is not truly random. But unless you did monstrously complicated measurements, you wouldn't be able to tell whether it's truly random or not. Okay? And so you can get pseudo-randomness produced, I'm told. I'm not an expert in the classical world. I'm not an expert, okay? But you, in principle, can get true randomness in the quantum world. The problem is, even in these random number generators, ultimately nothing is completely quantum and so on and so forth. So you wonder whether some of that true randomness gets corrupted, but you can come close to it. So pseudo-randomness is not true randomness, but it's close to true randomness. And we'd have to make it more precise what it means. But that's the basic idea.
Thank you so much, Sandeep sir, for your valuable knowledge. So now I would like to call upon Professor Umakant Rapol. He has the title talk, Atomic and Ionic Platforms for Scalable, High Fidelity Quantum Computing.
Good morning, everybody, and thank you so much, Dr. Sudhir and the Institute for inviting me to deliver a talk on some of the hardware aspects of quantum computing. Sorry. Okay, so I'm going to talk about two platforms today, and mostly I'll give you a glimpse of the ions-based platform and give you a short overview about the neutral atoms-based platform, which are used for quantum computing. So on the left, as you can see here, one second. So this is a schematic of the neutral atoms based platform where you see these dots, and then there are these bigger cloudy dots here. So basically this shows how you can make different qubits interact with them. And on the right you see this, okay, this video is not playing, but this is a toy model of ions which are trapped in an ion trap. So I'm going to give you a glimpse of this, and before starting my talk, I would like to acknowledge various funding agencies which have been involved in funding different experiments that happen in my group, and we are also part of the National Quantum Mission and also the earlier mission on the interdisciplinary cyber physical systems. And I do collaborate with Santanam and Rajesh and Srijit and some other people, but Santanam is here. And of course, this kind of tremendous efforts that have to take place in a lab, it's not possible by just one person. So there are so many students, my former students, current students, and new students who have joined very recently. So currently I have 4 students working on the 2 different platforms. 2 of them are working on the ions platform and 2 of them are working on the neutral atom system. So what we do is we use ultra-cold atoms and ions for doing various physics experiments, and in the recent times we have gotten into building quantum computers, but traditionally our lab focuses on using ultra-cold atomic systems for doing variety of these things, which are listed over here. So ultra-cold atoms are nothing but atoms that are cooled or held in free space or in ultra-high vacuum using electromagnetic forces. Either it could be from light, or it could be from electric fields, or it could be through with magnetic fields. You suspend these atomic systems, atoms or ions, in free space. When I say free space, it's in ultra-high vacuum environment. Ultra-high vacuum, when I say ultra-high vacuum, I'm talking about vacuum where the pressures are below 10 to the power minus 11 millibars, and it's extremely low pressure. Where like for example, when the number of atoms or molecules per unit volume at such pressures is about 10 to the power 11 times smaller than the number density that you find in atmospheric pressure. Okay, anyway, so these atoms are suspended, and when I say low temperature, I mean these atoms probably are moving at a rate of at speeds of about millimeters per second. Comparing it with these molecules at room temperature in this room, they could be up to about 1,000 meters per second. So reduction in temperature essentially is reduction in kinetic energy of these molecules. And then, of course, there are more rigorous definitions about what temperature is, but you can assume that if you reduce the velocities of these molecules or atoms, you're essentially reducing the temperature. Same with solids. So when you're reducing the vibrational energy of these atoms that are arranged in a periodic lattice inside an atom, inside a solid material, you are essentially reducing the temperature. Now, using those atoms, you can do things like you can build atomic clocks. You can arrange these atoms in periodic arrangement, like putting eggs in an egg basket. You can actually rearrange these atoms in a two-dimensional or a three-dimensional lattice kind of a structure, and you can do quantum simulations, essentially looking at what happens, simulating the physics that goes on in solids, for example. Like, for example, if you want to understand superconductivity, or if you want to understand semiconductors or any other exotic condensed matter system, it's very difficult to actually understand what goes on with all the details that need to be put in, because we don't know all the details that need to be put in. We simplify, physicists simplify these systems to simple Hamiltonians, and then you can either simulate them on a computer, which might take enormous amount of time, or you can use these cold atoms in optical lattices and simulate them. Then you can use the wave-particle duality of matter. Like, you can use these ultra-cold atoms at very low temperatures, use them as waves and do interferometry. Instead of light, you use atoms and do interferometry and gain in sensitivity. In our group, we work on these four aspects. We are building atomic clocks. We are doing some sort of quantum simulations. We also do atom interferometry, which is used for measuring gravitational acceleration to very high degree of precision for various applications. And on the slightly more fundamental side, we look at physics of Anderson localization and so on. And these are the five different problems. The first one is basically each of this dot here, what you see, is basically a giant matter wave packet. It's a Bose-Einstein condensate, and you can use that to simulate the physics of, say, Anderson localization. The second one is putting these atoms, confining them in two-dimensional lattices, and also use those same atoms. Like in this case, we use strontium atoms to do two problems: to build node for quantum information transfer from one location to the other, and the other project is building an atomic clock using strontium, which has an extremely narrow line width transition, which can be used for building clocks which will not even lose 1 second in the entire age of the universe. Then we do matter wave optics, and using Bose-Einstein condensate, we either can make quasi-continuous beam of very coherent atoms here, for example. Like, this is a beam of so-called atom laser, which diffracts from a light grating, similar to when light is sent on a matter grating, it diffracts. This is an analog of light waves with matter. And today I'm going to talk about these ion trap quantum computers, where we plan to build trapped ions based quantum computer, where each of this dot is a single ion, light emitted from a single ion, and we can trap a single ion and up to 25 ions in our trap. And this blinking, what you see is basically the quantum state of this atom, of this qubit. Either it is in 0 or 1 state, which are basically 2 electronic energy levels within this atom, which are used for quantum computing. And you can also see some exotic structures of these trapped ion crystals. These are called as Coulomb crystals because the ions are kept away, they keep themselves away from each other because of Coulomb repulsion. And overall, there is a potential that confines and tries to put them inside the trap. So I'm going to talk about first this ion trap quantum computing. So this particular picture, I like this very much. Of course, you can find it from the internet. This is not mine. This gives a good landscape about the entire field of quantum computing. It starts with I will not go through this entire thing, but it starts with giving a pictorial representation of the difference between a classical computer and a quantum computer, down to what are the different platforms that the world is working on. And you have various things on this. On the algorithm side, what are the different things that are going on, potential applications of quantum computers. I'm not going to say that again because already a lot about it has been talked about. And I will focus on only these two aspects, that is the hardware platforms which are used for quantum computing. I'll tell you about trapped ion quantum computers, and if time permits, I will glance through the neutral atoms based quantum computer. So the basic criteria that one looks for when you look at, there are so many quantum mechanical systems, right? There are atoms, ions, there are different types of molecules, there are electrons, there are nuclear spins, and so on and so on. And photons, of course. There are certain basic criteria one has to look at when you try to decide which particular quantum mechanical system one has to use for building a quantum computer. So DiVincenzo gave a set of criteria for choosing a quantum mechanical system as your qubit. Of course, the basic thing is you should be able to decide or initialize what the initial state of the qubit is, whether it's in zero state, 1 state, or some kind of a superposition state. Your qubit should have all of these quantum mechanical systems always interact with the environment, and whenever you put the qubit from 0 to 1 state, it is not going to remain there forever. For example, an electron which is excited from one particular energy level, like say some ground state to some excited state, it's always going to decay to the ground state, because if not anything in the environment, there are something called as vacuum fluctuations with which the electron is going to interact with, and the electron is going to decay at some point spontaneously. So all this will lead to decoherence, meaning when I store quantum information, it's not going to remain there forever. There is certain amount of time. So you need to have long coherence times, which basically tell me that the quantum mechanical state in which my the quantum information is staying is going to remain for certain amount of time, the amount of time before which I will finish all the computing operations. Then, like in classical computers, the basic gate that is used as a building block for building all your memory devices or the microprocessor or the CPU or whatever is a NAND gate. From the NAND gate, you can build any type of gate, and from any of these gates, you can then build flip-flops or whatever. You can make a sequential logic circuit or a combinational logic circuit and build your processor. Similarly, for a quantum mechanical system, there has to be certain set of universal gates, and these gates basically are single qubit rotation, which Jens talked about in his talk, and there are 2 qubit gates, which are these controlled NOT gates. So you need to have this universal set of gates. Then at the end of
application of different types of gates, which is basically performing the computing, you should be able to read out the state of the qubits so that you get the answer of the algorithm that you have executed on that. That you should have the ability to do that, and your system should allow you to scale up the system to as many number of qubits as you want for doing a meaningful computing operation. In addition to that, if you are dreaming of building many, connecting or stitching together many quantum processors, like in classical computers, you build an HPC by just networking or building a cluster of many CPUs. If you want to do that to increase the number of qubits, then you need to have additional criteria, which means you need to be able to map the internal quantum state of a qubit onto some entity which will take that quantum information to another processor and thereby maybe entangle two quantum processors. So one of the things that we know is a photon can do that. I mean, can transmit information from one location to the other, quantum information. And there are, of course, waveguides and optical fibers which will allow you to do that for doing the distributed quantum processing. Broadly speaking, there are two classes of hardware in the world which are used as platforms for quantum computing. One class is these quantum optic systems where you basically use atoms and photons for using them as your hardware for computing. So there are atoms in optical arrays, there are ions which are trapped in time-varying electric fields, there are single photons that are generated using parametric down conversion, and so on. So for example, this picture, I will come back to it later. This is from a neutral atom quantum simulator, where each of this dot is a light emitted from single atom which is trapped in an optical tweezer, and the separation between each of these dots or each of these qubits is of the order of 5 micrometer. And the interaction, the 2 qubit gates that are needed for quantum computing that are achieved through large electric dipole interactions between these atoms which are created by some mechanism which I will come back later. Then you have these trapped ions here. Then you can have atoms which are trapped in optical cavities and so on. Then you have the solid state systems platform where you have electrons which are trapped in a two-dimensional electron gas, and then you create metallic fingers and make small wells where you trap single electrons and then manipulate them use them as qubits. Then you have of course the superconducting qubits, different types, fluxonium types or the transmonium types and so on. Now people are also thinking of using color centers, defects in diamonds, as qubits, because if you take diamond crystal and naturally what happens is that in some locations 2 carbon atoms disappear and they are replaced by 1 nitrogen atom and 1 vacancy. This forms a artificial atom, a kind of a system inside the crystal, and it's very immune to any environmental perturbation. These people are thinking of using them as as qubits. Of all these platforms, there are 3 of them which are currently leading, and they are basically going neck to neck with different advantages and disadvantages. The first one is, of course, the superconducting qubits platform, which we always hear about. Then the neutral atoms platform, though it began slightly late, it is catching up very fast. They have demonstrated more than 200 logical qubits now. And the trapped ions quantum computer, again, last year, they have shown like 98 qubits. Now, the number of qubits alone is not an important factor, okay? So larger the number of qubits doesn't mean that particular quantum computer is superior. I always give this example about when digital cameras came into existence, everybody used to talk about megapixels, 1 megapixels, 10 megapixels, and so on. Of course, just the megapixels doesn't decide the quality of a sensor, okay? There is optics around it, a lot of things which go around it, which make a better sensor. So similarly with this, there is something called as a quantum volume, which basically tells you, you have to take into account the ratio of how long the qubit is maintaining its coherence to how long you are taking to execute a single gate. So within the coherence time, if you can execute larger number of gates than some other platform, that might have a better advantage. Plus, every single qubit operation or a 2-qubit operation that you are doing, what kind of error rates do you have in that? So all these factors come into picture, and then even if though the trapped ion quantum computer is of lesser number of qubits, it is probably more advantageous for certain things, and so on. So one has to look at the, anyway, nevertheless, these three are basically the leading platforms. They are basically going neck to neck. Now I'll tell you a little more details about this ion trap quantum computing, but some of the things, if you don't understand, you can skip. I will also try to skip things that I cannot convey to you very well. So basically, what is a trapped ion quantum computer? It's basically you have physical ions sitting inside in free space, inside vacuum, held by electric fields. And here is a picture of 3 of those ions, 3 atoms. This is light emitted from 3 ions, individual ions, and they are staying away from each other, as I said, because of Coulomb repulsion. They are all positively charged, and they are held inside, they are held together with some kind of a confining potential, external confining potential. And you can imagine it as 3 of these masses which are connected with springs. If you push one of these masses, all 3 are going to shake, and there is going to be normal modes of vibrations. So this can extend up to as many ions as you want. Now, this is a simple model. Now, how do you trap these ions? These ions are trapped in what are called as Paul traps, linear Paul traps. So we basically have 4 rods, and you apply a time-varying field between these opposite pairs of rods. Now, if you just apply DC field, you can always think of saying that, okay, I have a positively charged particle, I create electric field such that my charge, whenever it goes in any direction, it will get repelled and it will stay in the middle. But that is not allowed by basic electrostatics, because there is some theorem which says that in free space, you cannot create a potential minima where you can confine a charged particle. So if you try to create that, the potential basically is like a saddle. One way you may get repelled, but the other way you will get pushed. So you cannot create a trapping potential just with DC fields. So what you do that, imagine if this saddle, you put a ball there, some marble in the center. It's going to roll down, but on this direction, it's not going to go anywhere. It will be pushed back. This is what happens to a charged particle in electric fields, static electric fields. Now, if I rotate this saddle along this axis, vertical axis, what happens is that when the ball tries to roll down, it's going to be pushed back again. So this is what you do. You apply time-varying field across these 2 opposite pairs of rods, and you create a field minima along the center of these 4 electrodes, so that when you put a charged particle there, it remains confined along the axis. And there are many variations of this. I mean, this is again, you fold those electrodes down and create surface traps where you create trapping potentials just above the surface, and people are using this geometry to create scalable ion trap quantum computers using micro machining or microfabrication techniques where these electrode sizes are few micrometers, whereas this 3-dimensional ones can be several tens of millimeters. Like, this is an example of a racetrack kind of a geometry of a surface trap, which was the earlier version of a trap by this company called Continuum, which is a spin-off of Honeywell. And one of the reasons, as I said, with ions is that they have very large T1 and T2 times, which essentially are measures of how long your qubit is keeping the coherence or storing the quantum information. The connectivity, if you want to build a scalable if you want to use large number of qubits, ideally you want each qubit to be connected with every other qubit, which means I should be able to execute a 2-qubit gate, which is basically an entangling operation for the quantum computing. I should be able to entangle any 2 qubits in a set of qubits. So that's the connectivity. And there are ways to scale this up. Now, where are we in terms of quantum computing? Somebody asked the question, how many qubits or what you need for, say, breaking the RSA algorithm. So this is a nice picture from this person, Sam Jacks, I recently came across. Now, if you want to do any of this breaking of these RSA codes, you need about tens of millions of qubits. The x-axis is the number of qubits and y-axis is error rates. Of course, these are in log scale. So you need to be somewhere here. Now, all the quantum computers that are being built, they are all in this gray region here. Okay, now only recently, last year's quarter, this Quantinuum has moved up because they have about 98 qubits now with error rates approaching 10 to the power minus 4 or so. So slowly the world is progressing and many of these platforms also will be in this green shaded region where you can start doing some useful computing. Now this is the same picture that I showed you earlier. Oops, I can't. Okay, so this is an example of calcium ion which we are working on. There are different other ions which are also used for quantum computing like beryllium ions, ytterbium ions and strontium ions. So this is a three-dimensional trap where you trap the ions in the center of this electrodes. This is an image from a electron multiplying CCD camera. Forget about all these energy levels. What's interesting is that, okay, these are all the energy levels of the electron when you excite it in the calcium ion. So this is the ground state and then there are many different energy levels. Some of them are used for actually slowing down these ions and making this Coulomb crystal like these blue lasers. And then this 729 nanometer transition, this is like, if you put this light, you excite the electron from this ground state to this excited state D level, and these are our qubit transitions. The qubit state of this electron is either in 0 or 1 or the superposition of these two is our qubit basically, that's the qubit transition. Now that there is another isotope of calcium which also allows you to work with microwaves instead of laser. It allows you to work with microwaves, which is basically the ground state itself splits into two levels by an energy difference equal to about the energy of a 3.2 gigahertz photon. So you have an accessible to microwave frequencies as well as optical frequencies to manipulate this qubit. The way these qubits are manipulated is, as I said earlier, for single qubit gates, it's pretty straightforward. You shine light at 729 nanometer. Of course, this is a very specialized laser. The line width of this laser has to be of the order of few hertz at optical frequencies which are about 10 to the power 14 hertz, because the lifetime of this excited state is about a second. So the line width of it is very small, in the range of millihertz or so. So your laser line width has to be very small, otherwise it will lead to decoherence. So you shine that light continuously. What you do is that you then transfer the state of the electron from this 0 to 1 and back to 0 and so on. You basically induce what are called as Rabi oscillations, and these Rabi oscillations are basically this. So you monitor the population of this excited state, continuously shining the light, and this population oscillates from 0 to 1, 1 to 0 and so on. Now this will tell me for how long I should leave the pulse on, light on, to change the state of the electron from 0 to 1, or should I keep it in for such a long time that I create a superposition of this 0 and 1. For example, if I shine this light for half a microsecond, I'll completely transfer the population. These are all single qubit gates. If I shine that light for only 0.25 microsecond, I create a equal population of 0 and 1. Basically, you create a superposition of 0 and 1. Now that's this. And then where are these, if you have more than one qubit, one ion, then they'll start vibrating. So if you excite one ion with the right frequency, you will start making the ions oscillate in the trap, as well as you can manipulate the internal state of the electron. So this you use for making 2 qubit gates. Now, if you look at the spectrum of the ion, it's not a single 729 nanometer transition, which is this carrier. Once it is in a harmonic oscillator, harmonic potential, there are all possible motional modes of this ion. It's going to vibrate it's going to basically oscillate in this harmonic oscillator. And when you look at the spectrum of that, you will get different side bands, meaning if the ion is oscillating, then, if you come with light of a slightly higher energy than the internal transition energy, you will start oscillating the ion. So you use all these different vibrational modes to execute these 2 qubit gates. So this is a typical picture of the lab of different places. There is an ion trap somewhere in the corner, a lot of optics and lot of control systems and lasers which are used to condition these ions, meaning to load the ions, to laser cool these ions, to create the RF electric fields of several kilovolts to be applied on this trap to trap these ions. So these are the Rabi oscillations of this single ion. So we are improving on this single ion Rabi oscillations. Currently, we have some interference in the experiment which is basically making this Rabi oscillation decay. So this is the decoherence that I was talking about. Ideally, for as long as you want, this Rabi oscillation should maintain a fixed amplitude as it goes with time, whereas here it's decaying. So this decay is basically the qubit is losing coherence as a function of time. The longer this decay time is, the larger number of Rabi oscillations you can get to do on the qubit before the coherence is lost. So that's where this long coherence times come into picture. Now our vision is to have about a working 10 qubit one by this year end, and that we will reach hopefully, and next year end we should have about 25 of them. And then we are going to move away from this three-dimensional mechanically fabricated structures to microfabricated structures so that we can scale up the number of qubits. Now this, if you compare with what is there out there, this is the state of the art now. Quantinuum is a company which has about 98 qubits, and the error rates are pretty small, and they plan to go to thousands of them in the couple of years. They can do it because they have very sophisticated microfabrication facilities which allow you to make these chip traps and so on. But in the quantum mission, the mission is also trying to build this fabrication facilities which can cater to different types of platforms, including superconducting qubits and these ion qubits and so on. Now, people have already started putting these quantum computers for testing purposes. Like this one is from the Innsbruck group where I had worked 20 years ago. They have about 20 fully connected qubits, and this number is what is important, the quantum volume that I was talking about earlier, which is decided by many factors, not just the number of qubits. Okay, how much time do I have? Sudhir, how much time? 2 minutes. So I'll give you a flavor about neutral atoms. In trapped ions, you had this Coulomb repulsion between the ions, which allowed you to use common motional modes to apply 2 qubit gates. Whereas in neutral atoms, if you bring 2 neutral atoms close to each other, the interaction between them is a magnetic dipole interaction at the most, and it is very weak. So you have to get them really close to like few nanometers, which is typically not possible. So what is done is you take a neutral atom and then you excite an electron to very large principal number. So if you take away the electron to very large n values like 50 to 100 or so, what happens is that the electric dipole moment of this atom becomes very large. So when the electric dipole moment becomes very large, and when you get 2 of these atoms close to each other, there is a very strong electric dipole interaction. So there could be the van der Waals interaction or the dipole-dipole interaction when you try to get them close, and the interaction is very strong even at distances of several micrometers. So you use that. Like for example, if you take 2 atoms which are in this very high n levels, they are typically called as Rydberg states, where the electron is essentially looks like a classical wave packet moving around the nucleus. And when you get 2 of those atoms which are in Rydberg state, in the excited state very close, try to get them close to each other, the energy of the system increases rapidly. So basically you cannot have two atoms simultaneously in the Rydberg state when you bring them close to each other because of this electric dipole-dipole interaction. Okay, this is what you use to build the 2-qubit gates in case of neutral atoms. Now if you compare the energies of interaction when you get these atoms very close to each other as a function of distance between the atoms, like this is in micrometers. For Coulomb, the Coulomb interaction is very strong. This is what is there in the ions case. Whereas if you take the simple atoms where the electron is in the ground state, the interaction is typically magnetic dipole-dipole interaction, and which is very tiny, like for example 0.1 in hertz in units of frequency, as opposed to 10 to the power 11 hertz for either the ions or the atoms where the electron is excited into Rydberg states. So the interaction becomes very large. So what you do is then you use this interaction to build these 2-qubit gates. Like, as I said, 2-qubit gates are universal, is one of the most important universal gate. Single qubit rotation is easy. 2-qubit gates are difficult. You need interaction. Now, one of the basic 2-qubit gates is what is called as a controlled NOT gate, meaning the state of the second qubit will change only when the state of the first qubit is in 1. The state of the second qubit does not change if the state of the first qubit is 0. So that's a C-NOT gate, controlled NOT gate, which is the most basic gate, and then you can break any other gates into single qubit rotation and C-NOT gates and build your entire quantum circuit. Just to give you a flavor of how this C-NOT gate is executed in case of two Rydberg atoms which are very close to each other is that this is a control bit which can have 0 or 1 state. This is a target qubit which can also have 0 or 1 state. And this is the Rydberg level where the electron is in the Rydberg state. Now, if the first atom's state is in 0 and you try to excite a Rydberg state, it won't excite because there is an energy difference. Now, if you try to do a full 2-pi rotation on this, if you take the electron of the second qubit from 0 to 1 and back, you're going to pick up a phase. Like you told some time ago, Sandeep told some time ago that when you do a rotation on the Bloch sphere of the qubit, if you do a full rotation, you will pick up half the solid angle that particular thing has extended, half of that solid angle you pick up the phase. So that's, okay, it's either geometrical or dynamical phase, I don't remember now. There are subtle differences between that, essentially related to, again, the effect of the Aronow-Bohm effect. So if you rotate it on the Bloch sphere by a complete circle, then you will pick up a 2-pi phase. Now, if the first qubit, the control qubit was in 1, and you do this Rydberg excitation, what happens is that the Rydberg level of the second atom is going to get shifted because that atom is not going to allow the electron to be excited to the Rydberg state. So this energy level shifts, and when you rotate, when you do a full rotation on the Bloch sphere, it's not possible to do that. So you don't pick up a phase. So essentially it's a controlled phase gate which can be converted to a controlled NOT gate. This is how you execute 2-qubit gates with these Rydberg atoms. This is these are the results from Harvard group, Mikhail Lukin's group, where they demonstrated about 48 logical qubits. Now they have moved on to 256 logical qubits. So basically what you do is that you take an array of optical tweezers, sharply focused light down to 1 micrometer or so, and you capture atoms from a cloud of cold atoms, which is generated with laser cooling. Then you create an array of these neutral atoms. Now, you store these atoms in a storage zone where you have all these atoms which are stored. You move the required pairs of atoms with optical tweezers so into a region where you want to execute the 2-qubit gates, and then you bring whichever qubit state you want to read out, you move them with an optical tweezer and read out. This moving of atoms, arranging of atoms is done by what are called as acousto-optic deflectors, where you put radio frequency and the light can be shifted. You focus this light onto the atom, and then by changing the radio frequency, you can actually move the atoms. So you have a vacuum chamber where you have atoms, and then there are microscope objectives which are doing this focusing of light and creating the array of these optical tweezers where you trap atoms. Then you have many other things, like either you can create a static pattern of these tweezers, and then on top of that you can superimpose a moving optical tweezer and pick up whichever atoms you want, and so on. And yeah, okay. So let me see if this works. Yeah, so this is how things are done. There is an entangling zone here where you bring individual pairs of atoms, you entangle them. There is a storage zone and there is a readout zone. This is actually a real picture, I mean, a video created from the real operations. I think it's done, yeah, okay. There are a couple of companies which have already started putting these neutral atom computers for use on the cloud. So one is from the French groups, Pascal, and there is the Harvard group, the QERA, and there is also atom computing which has come up now. Yeah, thank you. Any questions? Okay.
Hello, sir. You mentioned calcium-40 ions and their excitations. Sir, so the excitations are discrete, right? That means it absorbs light and the excitations occur. So how do we convert that into the qubit system you mentioned? Because if the excitations are discrete, how do we get a value which is superpositioned that is in between? Sir.
Okay. I will not get into the interpretation of quantum mechanics and the probabilistic nature. The way when we do experiments, what we do is that we, for example, we come with a pi/2 pulse, okay? Which means what? I want to create an equal superposition of 0 and 1. I do one experiment, I come with a pi/2 pulse, and I do a measurement. What should I see? Ideally, I mean, you want to see a superposition. The way the superposition is built is, if you do one experiment, you will not get anything. What you do is that you do 100 experiments, 100 times you give pi/2 pulse, and 100 times you do a measurement. Then what happens is that 50 of those times, you will see that the electron is in the ground state, 50 of the times it's in the excited state. So you get probability, okay? So on a single quantum mechanical system, if you want to get an answer in terms of probabilities, which is what is the quantum mechanics tells us, when I have a superposition of 0 and 1, the coefficients that are there, the complex coefficients of that 0 and 1 which is creating the superposition, they are telling me probabilities. So if I give a pi/2 pulse, I should get probabilities of half and half. This is what you get. 100 times you do the measurement, 100 times you do the experiment and measure, 50% of the times you will get it in 0, 50% of it in 1 state. Now if I give pi pulse, where I excite the state from 0 to 1 completely, I do this 100 times, close to 100 times I will get the state to be in the excited state. So the way in our experiments, what we do is we point the laser to any of these ions, and then we turn on the 729 nanometer light for whatever amount of time decided by the Rabi oscillation frequency, and you do a measurement after that. Repeat it 100 times or 1000 times to get these probabilities. We measure probabilities.
Yes, sir. Thank you, sir.
Yeah.
So in superconducting qubits, there's a way to implement Z-gate called virtual Z-gate. So is there any similar technique here? If I want to implement a Z rotation, pure Z rotation, how do you do that?
So what you do is that you basically play with the laser pulses and your blocks and your block sphere. So you break up your rotation around any axis into different rotations and you apply them to get the desired rotation. So to begin with, if I start with a block sphere where my state is pointing up, either 0 or 1, what I do is that I can come to the equator and then I can go around the equator and then I can rotate it to something else. So you can break it down to a set of rotations to get any type of gate. So for single qubit gates, basically.
There is no like simple direct way. Like in superconducting qubits, if I just change the phase of my microwave pulse, I can implement a Z-gate.
So here also you can change the phase of the laser to do all this.
But have people tried it here or?
Yeah, all kinds of gates are implemented with the qubits. It's the same thing. You change the phase of the laser using acoustoptic modulators. You can do that. That's how it is done.
Hello. So I have a question. You said that calcium element was used, calcium ion was used. So,
that is what we are using, yeah.
So there are specific way, which element you're using, you choose it specifically.
Yeah, so there are many criteria which goes into choosing a particular element. Since even neutral atoms or these ions, they all rely on techniques of laser cooling, which means you use lasers to reduce the temperature of these ions or atoms down to sub-microkelvin or microkelvin temperatures. Now, in order to do that, there are certain conditions on the availability of these transitions. For example, in this case, in the calcium ion case, we use 397 nanometer light. So you basically need to have a very fast cycling transition where you get very large photon scattering rate. Because every photon that the atom or the ion absorbs and re-emits is going to reduce its translational energy. Because the translational energy is carried away by the photon. So the condition is that you should have levels where there are closed transitions. In this case, there is some decay to the other levels. Many atoms have that. You should have a possibility of cleaning up the transition, meaning clearing that transition. You should have closed transitions. You should have the wavelengths which you can technologically generate those wavelengths. And also for computing applications, you should be able to have levels whose lifetimes are very large. Like for example, if I excite this electron from here to here, from S state to D state, since the lifetime is very large, it naturally allows you to do many, many things. There are many additional criteria that goes into it, yeah.
Hi. So I'm trying to understand, there are many systems which are implementing qubits, right? And is it true that these systems are fully convinced to be qubits? And if that is the case, what is the bottleneck in your case in increasing the number of qubits? What is the real challenge? When you are if you are fully convinced about a given process of implementing a qubit, so then how does it translate to increasing its number? I'm yet to visualize it.
Okay, so all the platforms that currently the world is going after, there are some, as I said, in very advanced stages where people are already started doing quantum computing, started implementing quantum algorithms, but which, because people have worked on them for so long, we have reached a point where we know what are the limitations for example, for scaling or for increasing the gate fidelities and so on. There are certain platforms where the promises are very high. For example, the single electron transistors, for example. Right now, we don't know how to make a qubit. There are ways people are thinking of making qubit of the single electron transistors, but if we can make the qubit, that the first step is a big hurdle. But if we can manage to make it with a good fidelity and all that, there are ways to scale up. Whereas other systems, scaling has certain issues in to increase the number of qubits. So there are a lot of advantages, disadvantages,
got
promises.
This, I got this, like when somewhere on the talk you went from 1 qubit to increasing the number of qubits. You just, I think you quickly mentioned that it's connected by increasing the number of atoms. Is it just straightforward increase in the number of atoms, or is it a little more than that in your case?
See, it is like, for example, if I want to give you the example of this, okay, this was a 50 plus qubits architecture. This is a surface trap, microfabricated. This entire length could be few hundred micrometers, the length here, from this end to this end. There, you can trap a certain number of qubits because that is decided by the electrode structures, technicalities in the design of the surface trap. That they overcame and made on a different type of geometry where they are now able to trap 100 of them. Now, there are problems if you have 100 of them together and you just want to connect 2 of the 100 at the same time without disturbing the other 98. You need to have a way to pick out those 2, take them away, do the entangling operation and bring them back in. So it all depends on what possibilities your chip design will allow you to do that. So a lot of parameters go into that, yeah.
Okay, thank you very much.
Okay. Done, right?
Thank you so much, Professor Umakant, for your valuable insights on quantum computing. So now I would so we will have a quick lunch break right now, and we will meet at 2:15 for the event. Thank you. So his title talk will be his talk title will be Onions, Topology and Quantum Computing. Just use the arrows to change.
Yeah, sure. Okay. Thank you. Can you hear me? Yeah. Perfect. First, of course, I would like to thank Sudhir for his kind invitation to come to Mumbai. Okay, let's share the screen. Perfect. And also for this perfect organization for this event, I'm very quite impressed. All right. So Sudhir told me to do something which could be like, listened by almost everyone. So I'm going to present something where there are parts which I'm not an expert on. For example, I'm not doing per se quantum computing. I know things about anion and topology. So of course, there might be some questions that cannot be answered as precisely as I would like, but don't hesitate to ask any question anyway. So today I will probably repeat what has been said this morning about the basic brick of quantum computing, qubits and entanglements. You have heard that many times, but I think that, the more you repeat, the more you remember. So it's probably maybe a different point of view. And then I will explain why, because this has been seen in the different talks, why protecting qubits against decoherence is important, and I will try to explain how it could be done by topology. Again, those ideas, they are already dating from like 2008, where the first paper came, a big paper, how to use onions to do precisely topological quantum computing. So I will just re-explain maybe things that change a little bit, but they are the same idea. So for that, I will have to explain, go back to basic many particle physics, so bosons, fermions, and what are onions with respect to those two. And then I will discuss the fractional quantum Hall effect, which is basically where you can find onions that were thought about and then discovered later, but this is still under very intense research. So this is really something which is far from being completely understood and also completely experimentally, let's say, proved. There are many questions which are left, and so can we use that for quantum computing? And I will try to conclude saying, does it work yet? Okay, spoiler alert, it doesn't, because I will explain that this is more complicated, so it has more promises for the future, but experiments are probably much more complicated, even compared to what it has been presented this morning, which are already extremely complicated experiments. So, quantum world, if you want to do quantum computing or quantum information and all the physics of 2D quantum materials, you have one first key ingredient, which is a qubit, and this has been explained this morning, that classical qubits, they can be either 0 or 1, so you can flip them or do then the logical gate about it. And qubits, they can be 0, 1, or they can be basically anything between 0 and 1, and this is what Professor Kaur explaining this morning, that you can rotate between 0 and 1 to get some superposition. For example, if you do 0 plus 1 square root of 2, this is like having a qubit which is in a state 1, but the state 1 would be not along the z-axis, it would be along the x-axis, so it's another way to see this qubit. So and you can manipulate that the way you want. So as it was explained also this morning, the fact that it can rotate easily between two states, this is an advantage, because then you can do quantum computing and faster than classical computing, but it's also a disadvantage in a sense that anything that will do this rotation will basically going to spoil your result. So you have to be able to control all these qubits, let's say, even more carefully than one has had to control classical qubit. Just to mention that the fact that we can be 0 and 1 at the same time, this is superposition, and this is the matter wave aspect of quantum mechanics. Okay, so there is a particular aspect of quantum mechanics, and entanglement will arrive at this stage, but then there is a matter wave. So actually, this kind of superposition and the interference that we have discussed this morning They can be done also with, like a wave on the surface, or you can use light, and you will get exactly the same phenomena, as long as there are no, let's say, interactions, and there is no entanglement, and the physics are actually quite similar. And many things which could then be observed in, like, for example, with classical light. And for instance, I think about Anderson localization. So how light is propagating in a disordered system. Actually, they were done in a much better way using matter wave. Okay, so they were cold atoms, and they were sent in some, let's say, a rough speckle, basically. And then people have been able to show precisely this Anderson localization, the fact that wave packets are localized in disorder, even though classically the particle should fly to infinity. So from that point of view, there are plenty of things, as long as you only use a superposition. It's not very different from just having a wave. Okay, so if you have only 2, 0, 1, 1, then your wave has only 2 locations or in 2 energy levels. But if you have more degrees of freedom, then at the end of the day, you go to the Schrödinger waves that you might have seen in your lecture, or you will be seeing in your lecture if you do quantum mechanics. But it's the same. Then the second key ingredient is entanglement. So this has been discussed on sometimes called quantum correlation. And the idea is that if you take a big system, okay, and a generic big quantum system, and you split it in 2, okay, and then you get these 2 parts very far away from each other, then the full system property you had at the beginning can just not be simply understood by knowing all the property of A and all the property of B. There are some correlation, which is called entanglement, or sometimes people are saying mutual quantum information. Those things are not completely identical, okay, so, but I will not enter into a specific details between the difference between mutual quantum information and entanglement entropy and stuff like that. But the idea is that there are some correlations, quantum correlation between the 2 subsystems, and this is also what will help to make quantum computer much more efficient than classical computer. Now, there is a bit of subtlety, is that if you take a classical system, so you take a system and you split it in 2, a classical one, you will still get some correlation. Of course, if you're at finite temperature and the system are far away, those correlations will be, let's say, decaying extremely fast. So after some time, A and B, they don't know anything about each other. But I don't want to say that if you take a classical system and you split it in 2, that there are no correlation between the subsystems. It's not true. There are some correlation, but the quantum correlation are a bit more complicated than this classical correlation. And I know that there have been a lot of discussion by saying, okay, which are the correlation which are purely quantum with respect to the one that could be just described classically. And again, these things I've heard, I'm not working on that, so it starts to be a bit subtle. Something which is true, and this is what I describe here by the famous Alain Aspect experiment. Maybe you've heard of it. And it was basically taking a system, splitting it in 2, and making some measurement on one, making some measurement on the other, and then precisely to probe this quantum correlation. And there is Mr. Bell, we say, okay, let's try to explain this weird correlation, because they can happen at infinite distance, by some underlying classical variables, or let's say classical information that I'm not aware of. Okay, so maybe by putting more information, so I think that, for example, my system are just like a spin up and spin down, so 2 states, 2 qubits, let's say, okay? But actually, there is much more information which I'm not aware of. If those information is put in a certain way, can that mimic the weird correlation I see in the quantum system? Okay, so that's the first idea of Bell. And Bell's inequality say, okay, you can have some correlation, but the quantum correlation will be higher. Okay, so there it's a question of level. So this is what also I'm trying to explain, that how to measure, which is like classical correlation versus quantum correlation. So it's a bit subtle. So Alain Aspect did the experiment, and he showed that the Bell's inequality were not fulfilled. So that was proving that first Alain Aspect was working on the quantum system, and then quantum mechanics was right. So there is no way to describe quantum mechanics by hidden variable, local hidden variable, and you won't get the proper entanglement between your two subsystems this way. Again, all this can be, well, there are a lot of people still working on these kind of things, and it's complicated. And just also, I want to make a remark about quantum mechanics because, well, we all say it's weird, and then there are plenty of, let's say, it's a bit mystic and something like that. So I just want to say, of course, when I learned it, I was a bit puzzled, like everyone. And there's one thing which is a bit difficult is all the math which are associated to quantum mechanics, so that could be a bit difficult to absorb at the beginning, but that's technical, I would say. And then there are things how to interpret quantum mechanics. And this is where it starts to be confusing because there are many different kinds of interpretation, and depending with whom you are discussing, the explanation will be different, and then this is very confusing when you start learning. And for instance, something which puzzled me a lot is that, well, this is like, physics, mathematics. If you look at Schrödinger equations, this is fully deterministic, and then at some stage you say, oh, but quantum mechanics is random. No, okay, quantum mechanics is not random. It just means that, again, if I could describe a particle and a detector fully with one Schrödinger equation, then the evolution of that will be deterministic. The measurement will be deterministic. There is no problem. The point is that my detector is a classical system. There is no way I can know exactly its state and describe it fully quantum mechanically. So I have to make some assumption. And it turned out that if you take a small quantum system and you make it interact with a big quantum system, then things start looking random simply because you lack total information about the, let's say, essentially the big classical system. Okay? And it took a lot of time and a lot of books to understand what these 2 points of view are compatible in the sense that the randomness of the quantum mechanics is more related to the fact that you are missing knowledge about the full quantum system, and then it looks random to you, and then you have to use this measurement principle that if you do a measurement, you will project on an eigenstate and so on, which looks a little bit weird from the beginning, okay, and not in accordance with the Schrödinger equation. Okay, just a parenthesis to say that after all these things, you get used to the quantum mechanics and quantum world is not that weird. Well, it's weird, but not that weird. All right. So if you have these both ingredients, now you can do plenty of things. So the thing which is probably the most, let's say, progress in quantum information and quantum is quantum cryptography. And as it was said this morning, this is working very well. Okay, so you can really use that. And in particular, it's very useful because if you have somebody who try to eavesdrop on your things, it will affect the system. And then you will realize that somebody is spying on you, which is not possible in a classical world. So that's one of the ingredients why it works also so well. And I think it works really like in practice. So people are really using quantum cryptography at some level. So then you have quantum teleportation. Okay, so again, we are very far from Star Trek in a sense that we are not transmitting matter. We are copying quantum information. Okay, so that's different. And it was very well explained this morning that you need entanglement. And if you have that, then you can copy information of one qubit to the other qubit. But this qubit is not teleported to another place. Okay, so now it means that if you want to be teleported, you have to accept that basically they have to know all your information about you, and then they will rebuild that information in somebody else at the other side of the universe. So be my guest, not for me. I like my body the way it is, even though, okay, whatever. And of course, the last big thing, and it has been evolving like mad for the past 10 years, is quantum computer. And as it is explained that what we call the quantum supremacy is that in principle it could solve things much faster than classical computer sometimes the gain is not always exponential, okay? So there are some situations where you get a better scaling, but you don't go from a very complicated mathematical problem, so NP to a non-NP problem. But nevertheless, it promises a lot of things if it is used for, let's say, proper and relevant things. You know, it's like the artificial intelligence. You can see that it's not so always used for the benefit of the world, but that's another debate. So in real life, qubits, so then we have seen already many of them this morning. So there was an excellent talk and very impressive talk this morning about trap ion, cold atoms. So it was very well explained that you have a great control, but scalability is more an issue, but anyway, you will learn a lot of things about doing this experiment. And this is basically Microsoft Quantum is working with that. Then you have the superconducting qubits, the first that were introduced this morning. So then they are reliable and then they are really scalable. And this is what is used by Google and others. And they are probably the best qubit as of today in terms of how many qubits we can do. Now this is where I start discussing a different kind of qubits because we know we need robustness because quantum computing relies on protecting the qubit, keeping entanglement, and those things are extremely fragile. So it means contact with anything, environment, finite temperature. I mean, you will lose that very, very, very quickly. So then you have tricks, as it was explained also with this majority bits or quantum error correction. So you make one logical qubit of many physical qubits and stuff like that. But then it means that the resource you are demanding and more difficult to get. So the idea is that can one protect qubit from decoherence and imperfection using something else? And this is where people had in mind that they can use topology. So topology, you know that there is a difference between a sphere and a donut with one hole and a donut with two holes. So and there is no way if you take the sphere and if you do only deformation that you can arrive to a donut. I say smooth deformation. Of course, if you pierce the sphere, you will get a donut, but this is not considered by you as a smooth deformation. Similarly, you have all the mathematics of nodes, okay, and then there are many different kinds of nodes which are well described by mathematicians. And here it's the same. There is no way to get from, let's say, the first node 3.1 to the on-node situation, but just pulling the string and something. You will have to cut the string at some stage, but this is not considered as a smooth deformation. So it means that all these things, they are immune to small deformation. So if the sphere got a little bump, or the donut got a little bump, or the notes, let's say you pull a bit the string, it doesn't matter, it's still the same note and it's still the same donut, okay? So the idea is that topology, from that point of view, is immune to small disturbance because you are really encoding the information in the fact that you have this note or that note, or you have this donut or the double donut. And what doesn't matter is really the shape of the donut, is how many holes you have typically. Okay, so something which is known to corresponds to this are anions, which are found in the fractional quantum Hall effect. I will come back on that. And people have said, okay, if we use anions, we know that they are protected by topology, which is a bit different from the one I just talked. So maybe then we will have the perfect qubit in a sense that, well, you can do whatever. Okay, not whatever, but you can do a lot of things, and then it will stay as it is for a much longer time. Okay, so just now I go maybe on something a bit more technical. So the two spiky or hairy sphere you see at the bottom is just to explain that in quantum mechanics we have a property, and typically this property corresponds to, if you let's say that here I plot the sphere, but the sphere could be considered as an infinite plane, and then you can map that to a sphere, okay? And then on each point of the plane, I have a property, and that property is presented as an arrow, okay? So the direction of the arrow say what is the local property of my quantum system, okay? Now the point is that depending on the phase of my quantum system, if I plot all these arrows, I could be one of this pattern. And the idea is that, for example, if I start from the middle pattern, where all the arrows are pointing outward, there is no way to take this pattern and get the pattern on the left by just moving smoothly the arrows. It means at some stage, if I do that, I will have a knot, and one of the arrows will have to be rotated by a full rotation, which is not considered as a smooth deformation. Okay, so it means that the middle airy sphere is not topologically equivalent to the airy sphere on the left. Okay, and this is the idea. So that this is the knot, let's say, in condensed matter. This corresponds to this local quantity, and the idea is that now the information is not just one arrow, is what is the full pattern of all these arrows, okay? And that will be that phase, okay? So now if the arrows are moving a little bit, but the full pattern is not changing globally, then my system is still in the same phase from what I'm testing in. Okay, so, okay. So boson, fermion, maybe you know, anions, probably less. Okay, so when we have many particles in physics, there are properties. What happens is that if you take two particles and you exchange them, okay, so you have 1, 2, and then you exchange these two particles. If you have classical particle, even if you take two identical, let's say, a sphere, the same color, of course you can follow, and you say, okay, if this one was there and this wasn't there, and I do that, then okay, this one is there and this one is there. So classically, these two configurations, they are distinguishable because you can trace where they're coming from. In quantum mechanics, you can't. This is a principle. Well, this is what's called spin statistics. So it means that these two configurations, I mean, they must be the same. So now if you are boson, it means that the state, so 1 and 2, they should be exactly the same. So they are symmetric. Okay, so it means you exchange any particle, you get the same, you get to the same state. If you have fermions, then it's fully antisymmetric. So if you change 2 fermions, then you get a minus sign. And if you change 3 or 4, then the sign is different, depending on how many permutations, how you did it. Okay? So that's the only possibility which are allowed if you are in 3 dimensions, basically. But in 2 dimensions, people realize, mathematicians realize that there is another weird particle that if you do this exchange, the phase, so which is either plus or minus, can be actually a complex phase in front of this. And there is nothing, the third dimension, basically, you can show that the statistical angle gamma can only be 0 or pi, and you have only the thing. But in 2D, you cannot unknot the 2D knot going through the third dimension, and that's why this phase can be anything. So these are onions. Of course, the problem is that we don't live in 2 dimensions, but when you go to the fractional quantum Hall effect, it turns out that all the physics is actually really constrained in an effective 2D things, and all the excitation, potentially, they could be behaving like onions. So just to remind you, the quantum Hall effect is that this is this Hall bar. You send a current I through that, and because you have a strong magnetic field, essentially your electron they go to the left, or if the magnetic field is strong, then they are even staying rotating at the middle. This is a classical picture, and then you can see that on both edges, then the electrons are just bouncing back on the edge, and if you do that, you will see that the current is only transported at the edge. And okay, I'm not going to explain all the quantum Hall effect on 2 slides, but the idea is that if you look, this is what has been discovered in 1980. It was extremely surprising, is that if you look at the Hall resistance, which is basically the resistance between the 2 edges, here, it has a plateau at integer value compared to the quantum resistance, which is h over e squared. And when I say a plateau, the guy was surprised because it was a plateau with like 8 or 9 digits. Okay, so it's not like approximately 1. It's 1 with like 8 0 behind, and the same. So extremely puzzling, because if you do a classical calculation, what you will get is basically a straight line. Okay, so there is no way to get plateau, quantification, and stuff like that. So, well, this has been understood, explained. And what is much surprising later is that people also found plateau at fractional value, which were more puzzling because an explanation for the integral quantum Hall effect was found. But then there was no way to get fractional value in that simple explanation. And then people realized that what's very important in that situation is you need the strong Coulomb interaction, and that's how at the end of the day you can get this fractional value. If you're interested, I can explain you why, but not on other things. And what is important is that if you look at the fractional quantum Hall effect, so typically the main theory are the density is 1 over m, where m is on, and these are called the Laughlin theory. So you can see that if you make excitations, those excitations, they are not electrons. So again, all these things are just purely electron in a metal, okay? If you look at the excitation, the charge of the excitation is just a fraction of an electron. So you as if you were cutting electron in bits, and then that would be the excitation. But more interesting is that people realize, well, at that point, it was conjecture that they have a statistical angle, which is pi over m, where m is the same number, and this is exactly the angle you get by exchanging two anions. Okay, that was predicted. Okay, and then after that, they get explanation for the other series and so on and so forth. Just to tell you that why this is still under a lot of investigation is that there are a lot of experiments which actually, the point is that if you see that the statistical angle and the quasi-Hall charge, they are both 1 over m. So it's very hard to tell when you see a fraction, when you measure a quantity, whether this is due to the fractional aspect of the charge or to the statistical angle. And even like 5 or let's say 10 years ago, there were obvious experiments for the charge, but there were no obvious experiments for the statistical phase. So this is still under a lot of investigation. So now there were recent experiments which show that, but this is for the simplest case. You can imagine for the more complicated case. Okay, so now those anions, they will be they are the quantity, well, they are like the holes in donuts. Okay, so they are like vortices in the electron fluid. And now to make, so there will be the bricks of the qubits, and the idea to do quantum operation, now we will exchange the anions, and this is like, braiding things, okay? And if you go from one state and you do some braiding, then you arrive to another state, and it will be like a gate applied on a quantum state. Now the problem is that the traditional anions is just a phase. So whatever braiding you do, you will always get back to the same state. And so it means that it's as if you are in the 0 of the qubit. So you can change the phase of the qubit, but you will never go to the 1 qubit. So you need something else to do the 1 qubit or to go to the 1 qubit. And so basically we need anions with some internal labels, okay, something which tell you that anion can be a 0 or a 1. Okay, I'm just hand-waving argument. And this has been conjectured by Moore and Reid at this filling, which is 5 half, which is surprising because this is an even fraction. Almost all the fractions are on the numbers. And those anions are called non-abelian Ising anions. Okay, alors non-abelian, again, this is just a fancy word, okay, and quantum mechanics like fancy word, just to say that when you do two things, if you do A and B, it's not the same thing as doing B and A. And that's it, okay? So just saying that things are not commuting, or if you do it. And this thing is completely classical. For example, the braiding, okay, if you are just braiding your hair, okay, my hair too short, but if you take hair and you braid, then you will see that the braiding will depend how you do that, okay? And this is completely classical, okay? Rotation also are completely classical. If you do first that rotation and then another, and you do the opposite, you will not end at the same point. So, but okay, we like to call that non-abelian because, we do something mathematics. And in particular, people have shown that if you have 4 anions of this phi half, you can do 1 qubit. I'm not explaining exactly how, this is a bit complicated. And in particular, now, for example, if you take these 4 qubits and you will exchange the anion 2 and 3, you will get this matrix, and let's say it just means that this is a way to go from 0 to 1. Okay, so if I start from 0, for example, if I start from 0, I will go to a superposition. We'll have 1, 0, and minus I times 1, and if I start from 1, I will get this opposite. So it's just saying that if we exchange 2 and 3, this is like making a mixture between 0 and 1. So we can do gates with braiding Ising anions. Okay, so mathematically it's simple. Now I just want to make a parenthesis, because if you start reading books about topology in, let's say, condensed matter, for instance, there is topology and topology. Okay, so the one I just discussed is really the hard, true topology you get in 2D. Okay, so bulk anions. So it means that, sorry, where is the pointer here? So if you look at your system, you have a ground state, and all the excited states, they have a much higher energy, so the normal excitation, okay? And now if you look at anions, okay, first you can see that they are all degenerate, which is nice, because then if you want to make braiding or gates, everything stays at the same energy, and the fact that they have some energy, this is protected by the topology, okay? As long as your system is large enough, blah, blah, blah. And the second point is that those anion excitation, they are still very far away from the overexcited state. So they will be not contaminated by being coupled to the excited state, which will lead to leaking of your information, okay? So this is genuine protection, this is genuine topology, but it's very hard to control because those systems are very difficult. Magnetic fields have to be very high and so on and so forth. Now there is what we call, let's say, a weak topology, and typically this is what people see in quasi 1D systems. So something which is used, I will come back on that for superconducting quantum computing. You can see that if you have a topological superconductor, okay, this is something which is topological, and then on the other side, there is a vacuum, okay? And because you have an interface between something which is topological and something which is not, then you must have a particle which is a bit special. And in that case, it's a Majorana zero mad. The problem is that, so you can do also braiding with those Majorana topological things, but these Majorana, they are only protected by a symmetry. Okay, and it means that as soon as this symmetry is broken, all the degeneracy and the protection will be lost. So it means that you really rely on having this symmetry of the system, and that makes it much more difficult and less robust to think. And one difference also is when we were discussing entanglement. If you take a full system, okay, and I just look at the entanglement between B and the small system A, okay, there is something which is called area law. It means that the entanglement between the two is essentially proportional to the surface, the length of the boundary. So it means that if your system A is getting smaller and smaller and smaller, this entanglement gets weaker and weaker and weaker. Whereas, if you go to a genuine topological bulk system, this area law is broken. It means that at some stage, if your system A becomes too small, the entanglement remains finite. So it really shows that there is some property, entanglement, which is really strongly distributed among the full system. And this is why you are protected, okay, topologically protected. It's not just this energy or level I show, which is a factor, but also for the entanglement itself, there is an additional protection, which is seen by the fact that the area law is broken. Okay, so now I'm almost done. Just to say that, well, there are some people working on superconducting topological quantum computer. Not superconducting, well, yeah, in that case here. So the one which is known is Majorana 1 by Microsoft. So they say that they have the first functional qubit in 2025, and they are precisely using these edge Majorana fermions. So they are much easier to produce than the anion from the fractional quantum Hall effect. But there are some controversy whether they were really having Majorana modes or if it was something else and so on and so on. But nevertheless, they are trying, and whatever you do, you will learn. And also something I like to say is that when you do research in physics, sometimes you have like a serendipity, so it means that you are making other discoveries that you are not imagining that you are really going to have. Plenty of things have emerged from that, so one never knows. Okay, so go on. So then there is a quantinum, so it was also mentioned this morning. So here they are using trapped ions, so the same trapped ion we saw this morning, to engineer something where the excitation will be non-abelian ions. So it's not the fractional quantum Hall effect, but they are mimicking that. So again, because this is much more controllable, maybe they will learn how to make gates in a better way within this system. And now there are some other theoretical proposal with some 2D system, and if you put 2 layers, a bit of angle, then the property of that system say that you might get also excitation that looks like a non-abelian ion. So this is very new, this is theoretical, so nobody has really done the experiment on that. But again, there are a lot of things to explore, there are a lot of things to engineer, so as everyone said this morning, there are plenty of opportunity, and I just learned that India now is putting a massive amount of money into quantum computers, so feel free to go into that direction. I'm pretty sure there will be a lot of jobs there. And engineer cannot be replaced by artificial intelligence. I mean, so that's a secured job. Okay. How much time do I have left? Sudhir is gone. Should I stop? Okay. Okay, just to summarize that, basically, there are a lot of things. So on both the side of, let's say, quantum computing, but let's say there is still a lot of things which are done on that subject in physics in the lab, because this fractional quantum Hall effect is far from being understood. Okay, and I thank you for your attention.
Sorry, thank you for a great talk. And I apologize for a slightly technical question, but if I can just go to that slide where you had, the 2 fractional quantum Hall and then the edge. Yeah. So just so I make sure, by your comment here, you meant there's a topological entanglement entropy in the fractional Hall. See.
And that's why, I mean, I had to rush. These states actually are called symmetry-protected topological states, just to make a difference between the true topological state. But sometimes this is written at the beginning of the paper, and then the confusion, and then it's a bit, okay, people forgot that these topological properties are not exactly the same, and this is a big, from the quantum information, this is a big signature of that. And this has been, at least, the RLO, of course, has been seen many, many, many times, of course. Yeah.
I see. Thank you.
So I'm curious to know, like one of the places in condensed matter where we see a lot of topological entities is in liquid crystals. Liquid crystals. You see a lot of topological entities, and which can be precisely controlled. Are there any thoughts in this direction, like, and these defects are very particular to, the phase where you are in. Like, for example, a nematic or the polar order, everything can be very, very precisely controlled. And I think if there are some theoretical or at least those attempts in this, in your knowledge, I would like to know.
Okay, I don't know. I can try to find some information, but it's true that, well, the picture they were taken, I mean, this hairy sphere, they were taken also from old people discussing about skyrmions and meron and stuff like that. So I don't know whether the people here have tried to think about using that as a qubit. The problem is that typically those spin texture, they take space opposite to the ions, where the size typically will be typically the magnetic length. So you can put much more of them on a smaller plate. So that might also be the difficulty. But I don't know, honestly.
Thank you.
Hi, I know you mentioned before that it's complicated, but could you explain in brief how 4 anions could make a qubit?
No, no. I can, but not in 2 sec without a blackboard or a piece of paper and so on. We can discuss that later if you wish. It's a bit technical, and I will have to enter into some much more details of the fractional quantum Hall effects. So, sorry.
Fair enough.
So,
Thank you.
in principle, I can, but in practice.
Yeah, can you go back to that slide where you have the picture of that device? Yeah. Any comments on what was actually achieved there?
So here, as far as I remember, they have only the thing on the left. It's just a single qubit, so there was no gate, and they were able to read out whether they were in 0 or 1, basically. So they claim that they have a functional qubit. But as far as I remember, at that time, they didn't really do even single qubit gate or something like that. It's really like preliminary, and even the results, again, this is a controversy, is whether the effect, so there was some things, so experimental result, but whether this was due to really Majorana edge state or some kind of overstate, like Andreev state. There were a lot of heated discussion on the net.
Okay, thank you.
So thank you so much, Professor Benno.
Hello, sir.
Yes.
I have a question that in every phenomena or process in physics or chemistry, you see changes happening or something is, you can see physically, you can observe what is happening there at any level. But what happens here, like how quantum entanglement is happening? How can we observe, or what experiments by which we can imply that it is?
No, this is an excellent question. It means that you have to have observables, something that you will be able to measure that will show, or that will be a marker of this entanglement. So for instance, you could imagine that if you have, and this has been done, for example, with a Bose-Einstein condensate or things like that, is that if you can physically split the system in two and then measure some quantity, then you can measure, for instance, the entanglement that were in your system. So now it's like, you know, those observables will be like some kind of a microscope to see things which are extremely small. So now, depending exactly on the physical system you are studying, whether they are cold atoms, ions, then the quantity you will be measuring will be different. Okay, but then the idea is that if you measure that quantity, whether there is entanglement or not, the value will be different. Okay, so you need to do a bit of theory before to do that. Okay, so but there is no entanglement meter, if you wish. So there is nothing that you can put to measure directly the entanglement. You can just measure it by measuring some observable. Okay, so but this, for instance, this has been a lot of discussed a lot. For instance, when Alain Aspect was making this Bell experiment, what he was measuring at the end, he was collecting photons and measuring the polarization of photons and stuff like that, and this was related to the entanglement at the beginning of the system. Okay, so, but there is no generic answer to that.
So is it just more theoretical, or
No. What I mean is that for all these systems, there is always a way to measure how much entanglement, and even that, there is another problem in quantum information, is that there is no absolute measure for entanglement. For 2 qubits, yes. So all the measures are more or less equivalent. If you start having more qubits, then the degree of entanglement can strongly vary from one measure to another. So even the mathematicians say there is a problem there. But nevertheless, you can have quantity whose value, when you do the measurements, now with classical apparatus, will tell you how much entanglement you had within your system. Okay?
Thank you. Absolutely amazing talk. I did not understand most of it, but
So I don't know how amazing it is.
my question is that when there are two particles that are entangled, there is some sort of information that is common between them, and that information, I am not sure how it is stored, where it is stored, or what information that is. Could you kindly give your comments on that?
I think this was a bit explained this morning. Is if you take some quantum states, okay, and there are some, and if you have only 2 qubits, basically you have 0, 1, and 1 of 0. There are states, if you write them, there is no way that this state can be written as a product of state 1 times the product of state 2. So product of state 1 will be any 0 plus 1 for the qubit 1 times, for a tensor product, times any 0 plus 1 of the state 2. And if you do this multiplication, you will see that there are some states which cannot be written that way. And then they are entangled. Okay.
My question was that there is this information, right?
Yes.
Where is that information stored? What kind of way it is stored?
Now it starts to be a subtle question in the fact that how it's more, you have information, and how you store information into the entanglement of the qubit. Now that depends, okay, now I approach the limit of my expertise. So it depends on how you will proceed your gates and things like that. Okay, so that's all the problem also that we have discussed, is that even if you can do the gates, how you encode and how you decode the information to the quantum system.
Thank you.
So, thank you, Professor Benoit, for your valuable insights. So now I would like to call upon Professor M.S. Santhanam. He is going to give a talk on promise and gaps in quantum machine learning.
You have a connector for this USB?
So you have to USB charger. Do you want?
Not charger. How do you connect this?
So you just.
Is that okay? Okay. Good afternoon, everyone, and it's my pleasure to be visiting here again. I come here, if I remember, about 2-3 months ago, I think, and thanks to Sudhir Jain and Somaya Vidyavihar University for this introduction and wonderful hospitality. So my title is Promise and Gaps in Quantum Machine Learning. So it's going to be about quantum machine learning. But you don't need to worry if you don't know either quantum physics or machine learning, because
I think all of us are in the learning stage at different levels. So this is going to be an overview plus along with my own opinions put together. Let me start with a kind of very broad top level view of what the classical machine learning does. At a highest level of abstraction you can think of, you have some data, possibly, whatever it is, images, numbers, and so on. And you have some machine learning model which learns from the data and you get the output. So quantum machine learning is similar with a small twist. So you do have data, and the data is same thing as what you would use in a classical machine learning paradigm. In the sense that just because you are using a quantum machine learning model, your basic data cannot change. No? If you want to use data of maybe, let's say, weather data is weather data, ASCII data, numbers, and so on. So that still remains the same, except that your quantum machine learning model now can only talk in terms of quantum states. So which means that you have to convert your data, something like B0, B1, B2, let's say, if those are the kind of data that you have, it needs to be converted into states. And that's what is called the encoding part. So take your usual data, convert it into quantum states, and that is accepted by a quantum machine learning model, and it does some process on it, and hopefully it is useful for us. And then you convert and it spits out quantum states again. And again in the reverse mode, you again convert from quantum states into numbers that you can understand and hopefully use it. That's your output. So this process of changing from data into quantum states, typically into superpositions of quantum states, is usually the encoding part, and finally there is of course the decoding part as well. So typically when one talks of these classes of algorithm, you can imagine four different scenarios as it is shown here. So where your data is classical and your model, let's say the machine learning model is also classical, that's the usual typical machine learning paradigm. Whereas you can have a situation where the data is quantum, but you are using a classical machine learning algorithm. And if you see journals, there are many papers of this type where data is quantum, you're dealing with quantum states, and you want to extract some useful information, and typical classical machine learning algorithms will work. But what we really mean when we use the word quantum machine learning is the other two classes, where the data is classical and the algorithm is quantum, or the data is quantum and the algorithm is classical. So these two is usually called the core of quantum machine learning part. And again, at a very broadest kind of level, one can think of, I mean, again, even though quantum machine learning is in some sense an emerging area, but you will see hundreds and hundreds of papers out there, and there is even, at least I know of one good authoritative book on the subject. So there are already, ways of classifying what kinds of algorithms and so on. So there are, one class of algorithm is all these basic linear algebra algorithms, which are things like, for instance, diagonalization, or finding inverse of a matrix, finding eigenvalues, eigenvectors, and so on. And then there are kernel-based techniques where you replace dot products with kernel products and use them. They are in some sense efficient. And then there is whole class of variational algorithm where there is some parameter that is varied. So that parameter itself is learned as part of your algorithm and use that in some setting. And of course then there is whole class of quantum neural networks as well. And what is the main USP behind quantum machine learning is that it could make some learning tasks faster. It can make them more expressive or maybe more efficient as well compared to classical machine learning. So you can see, for example, speed ups for very hard computations, typically, as it has been pointed out many times, using entanglement and superposition, and which means that it can evaluate many possibilities simultaneously. And QML can handle exponentially large feature spaces, which means that, which arises from the fact that quantum systems themselves live in large Hilbert spaces. So if you have n qubits, the space is like Hilbert spaces of dimension 2 power n, which means that this is a huge enough space to compute rich feature maps that's required for machine learning purposes. So you don't need to really allocate as much in terms of qubits. You can do better optimization problems, and it's particularly good for quantum data. So if you probably have an experiment or even simulations where the output is already a quantum data and you want to work on that, these provide kind of natural paradigm to work with. And then there is another class of hybrid classical quantum learning. Here the idea is that the more difficult parts of the algorithm is left to the quantum, and relatively easier parts which is best done by classical computing. For instance, often the optimizer is classical because there are very wonderful optimizer algorithms for learning the parameters. That is left to the quantum, but rest of the evolution is done through the optimizer is left to classical, and rest of the evolution is done through quantum algorithms. Okay, so I'm going to only concentrate on one part of it to tell you that there are very wonderful algorithms which provide speed ups. So I won't be able to, in the given time, actually discuss many different types of algorithms illustrating each and every one of these claims. So the one promise part of the quantum machine learning is that at least there are class of quantum algorithms which can solve certain classes of problems faster than classical algorithms. And I have put a star there to indicate that it comes with so many caveats that unless you are aware of that, you shouldn't take it as the statement that there are problems which can be solved in a much faster way. So I'll come to these caveats a little later. Okay. But the first question is about how do you measure the speed. After all, you will tell me that if I use a 10-year-old computer, that's slower than a computer that's probably that may be just something that we bought a few days ago. Clearly, that's not the way one should measure the speed of algorithms. So this is, as it was referred to in the morning, a part of what is called computational complexity. So to give you a very diluted version of what this computational complexity is about, I have this graph here which shows the time it takes to solve a particular problem, and on the x-axis is size of input. So it depends on how the time taken to solve increases as you keep increasing the size of the problem. For instance, just for illustrative purpose, if you look at these two maze problems that is shown here, the first one is a very small maze, and even by sitting there you can figure out if I start from that red point how to reach the green point. It's very simple. But on the other hand, if that second maze, if that's the problem I give you, then it's going to be very hard. It's going to take you longer time to figure out how to go from a start to the end point. So clearly, as the size of the maze increases, the time taken is increasing. So what we are interested in figuring out is how does it scale as the size of the problem increases. So that is what that graph shows there. So broadly, again by diluting all the, this one, hopefully there are no mathematicians here. By diluting all that, so there are two broad classes of problems here that you can identify. One which increases exponentially with size of the problem, e power n, and this is the worst case scenario or the kind of nightmarish scenario where as your size of the problem increases, you will end up with the situation where you can't solve the problem even till the end of the time of this universe. But on the other hand, a more convenient scenario is where it increases in a polynomial sense. It goes as n to the power mu, that blue curve there, where as it increases, it's only increasing polynomially. This is something that you can accommodate and work in our real computers here. So for instance, matrix diagonalization, the computational complexity goes as n cube, okay, where n is the order of your matrix. So that's a polynomial time solution. So which means that even if you take a large matrix, which is what we do when we solve many quantum problems, you construct a large Hamiltonian matrix and diagonalize it. You can hope to wait for maybe 1 day, 2 days, depending on the size, and finally you will get your solutions. And another problem is searching an unstructured database. Let's say you have a database of all kinds of data which is not ordered in any particular way. That's an unstructured database. And you probably have to just find one element in that large database. So the time it takes is of the order of n. So these orders, these tell you how complex the problem is to solve. Order of n cube means time goes as n cube. That's what it means. So we'll use this terminology now. So to give you two specific examples of what I call the promise part. The first one is a linear system solver, or the quantum algorithm for this is the HHL algorithm, or named after the authors Harrow, Hasidim, and Seth Lloyd, based on this paper in 2009. So the linear system solver is something that I think everyone has done in maybe 8th, 9th standard. You take two equations with two unknowns, and the question is find the two unknowns, x and y. Okay, it might look like you need an strange that you need an algorithm to do this. So if you're doing only with two unknowns and two equations, you don't need such heavy duty algorithms. But like in when you solve many partial differential equations, for instance, finally you can reduce it to a point where you need to solve a linear system. And there the linear system is like it can have million unknowns, and the size of the matrix A that you will be dealing with will be a million by million or even more. Okay. So there it's no more possible to sit and work with the paper and find the unknowns. So you need some algorithms. And the best known classical algorithms typically take of the order of n square to n cube. That's the kind of time complexity. On the other hand, the quantum algorithm due to HHL promises a solution in log n time complexity, which is, so k, let's not worry about k, it's called the condition number of the matrix. But the point is that between, let's say, n square or n cube to log n, there is an exponential advantage that you gain in using the quantum algorithm for solving this problem. So this is one of the problems where it's a case of proven exponential advantage. And this is something that's very useful in a large class of problems that is very useful in an industrial context, simply because PDE solvers are something that are backbone for many industry problems. So here, for instance, you go back and try it out on a simple problem, and this is the quantum circuit for solving this problem. I'm not going to explain the quantum circuit now, given the lack of time. But so let's say this simple problem that we have, the x, which is basically the unknown vector that we have to find, is 3 by 8 and 9 by 8. And what this HHL algorithm actually gives you is the ratio between the first and the second element, 3 by 8 and 9 by 8. So it gives you 1:9, which is the correct answer. So, but there is, okay, so in fact this is a full implementation of these circuits. So I'm not going to, as I said, talk about the circuit itself. But what I want to point out is that now if you actually implement this first on a simulator, you take it to a simulator which does not have any, let's say, noise, does not require error correction and so on. The result that you will get is what is shown in the left side bar chart. Okay. So you get something that's very close to the expected result, which is 1:9, but here you get 1:8.95. But on the other hand, you actually run it on a real quantum hardware. In this case, it was run on a real IBM hardware. And the result that you get is 1:2.57, which is very far from the expected result. This also tells you how crucial error correction is if you want to get something reasonable out of quantum computers. Okay. But of course, there are error corrected version of this. I don't want to convey the impression that even a simple problem like this cannot be done on a quantum computer. This is just to point out that naively, if you take these algorithms and put it on a quantum computer, you might end up in a situation like this, which means that you need to apply appropriate error correction algorithms to get closer to the correct result. Apart from this, this is run on what is called the gate-based quantum computer. In this case, it was the superconducting qubit-based quantum computer. There are also experimental demonstrations of this HHL algorithm on photonics systems. But again, that's a topic for itself. But I just wanted to point out that these classes of algorithms can be realized on many different types of quantum hardware. Okay, the first one is not, even though it falls under the class of quantum machine learning algorithm, if you're carefully noticing it, it doesn't really have the core machine learning component to it. It was simply a linear solver. I know you might tell me, I've been doing this since my 10th standard, suddenly where did machine learning come in there? Okay, it didn't have a machine learning, true. But here is one which really has a machine learning component, the support vector machine. So this is a workhorse of modern machine learning algorithms. Pretty much anything you do, you will have to do some classification of data, and probably the go-to algorithm is the support vector machine. And there are, again, even within the classical machine learning algorithm, there are whole lots of different approaches to support vector machine. So it's a supervised machine learning algorithm. The idea basically is the same for those who don't know. So let's say that if we have this data that is shown there, x1 and x2 axis, you have this data. There are two types of data. One is in blue color and other is in red color. The whole idea is to be able to draw that red line that is shown there so that you can classify both the sets of the data. That is what the support vector machine does for us. So in fact, more carefully, it tries to optimize or maximize the distance between the two classes. That's your support vector machine. So the classical support vector machine, of course, you have the data which is presented in the form of series of vectors xj, and then there are labels to it because it's a supervised machine learning algorithms. You also have to give it the labels, and that's your x vector j and yj. And the typical kind of workflow is that you convert the classical support vector machine into what is called a quadratic programming problem. That means that it's actually a quadratic equation with some constraints thrown at it, and this can be solved in order m square into m plus n time complexity. But there is a quantum version of support vector machine which solves the problem in log mn complexity, and as part of the solution, it uses HHL algorithm as well, and a very efficient inner product evaluation. That's where that kernel techniques are used in this case. So this is again an example of exponential speed up that is offered by quantum machine learning algorithm. So I gave these two as simply samples. In fact, there are a whole lot of dozens and dozens of algorithms which provide varying levels of speed up. Every problem need not give you an exponential speed up. So for example, online perceptron, which is also a classification technique, can give you a quadratic speed up over classical technique, or for instance, quantum principal component analysis. So principal component analysis is again one of the standard techniques in statistics and machine learning. And quantum PCA also offers you an exponential advantage over standard classical PCA techniques. So at least I know of, in fact, there's a website called quantumalgorithmzoo.org, I think, which gives you at least about 120 to 150 different algorithms, lists the speed-ups of various quantum algorithms. So if you are interested in this, that is one place you should look up and see. Somehow I'd forgotten to put that website here. And in terms of applications, clearly it kind of straddles many different places, ranging from drug design, predict new properties of materials through quantum simulations. It can also help in error mitigation for quantum computing, in quantum sensing, and in a whole class of optimization algorithms. So I think the applications are really in some sense endless. So so there is a whole, as I said, there are lots of different quantum versions of algorithms, but at another level you could say that there are some classes of algorithms which are waiting for a big fault tolerant quantum computer to appear, so that you can run them with certain level of confidence. For instance, the linear system, which is the HHL algorithm that I spoke about, is not something that you can work with today for very large linear systems. You can do a 2x2 or a 3x3 or maybe somewhat bigger, but if you are going to present the system with a million by million linear system, it's going to fail. So that is again one thing which is waiting for a fault tolerant quantum computer or clustering algorithms. But on the other hand, there are a whole lot of other algorithms which can make do with the current NISQ architecture quantum computers. Plus, in addition, you throw in, let's say, the classical high performance computers that we already have. So these are called the hybrid approaches. So there is entire class of variational quantum eigensolvers or quantum approximate optimization algorithms. So these are the classes of problems where the best of both the worlds is used, both the classical computing and the quantum computing. And so the typical variational quantum circuits work like this. So that zero stage that you see on the left, that is where the data is encoded. And then you have a collection of quantum circuits which are parameterized by theta, that is shown there, and that's the parameter that you need to learn. And typically what happens is that the parameters theta are basically sent to a classical computer to learn, subject to the measurement values, measurement which are done after a quantum evolution. So this continues for several rounds until you, in some sense, you meet the criteria set by some loss function and so on. So this is like a basic template. You can use this for many different problems for constructing a variational solution out of it. So maybe I'll just take 2 minutes to talk about one approach that we have been doing for the last 1 year or so. This is what is called a reservoir computing approach. So here what is done is you use the fact that you studied these dynamical systems for ages, and there are some advantages that we can reap out of it. And in fact, it might come as a surprise that you can actually use dynamical systems to compute. So a typical machine learning system consists of neural networks in various architectures. You connect it through various architectures and so on. There is an input, and finally you optimize the connection parameters and get the output. But here, those neural networks are replaced by dynamical systems. So the dynamical systems could be anything from, say, a pendulum or a harmonic oscillator or anything like that, anything that one studies in physics or anything that you can invent. So put them together in some connection topology like this, and this can do learning work for you. This can be a template for machine learning. Okay. So what is the advantage, you can ask? Like, I've been doing it with neural networks, now why do you force me to learn physics and put dynamical systems there? The reason is that you can see the way this template is shown here. There is nothing to learn from the reservoir itself. You construct a reservoir with whatever parameters you want. You throw in as many dynamical elements as you want. But the only parameters you have to learn are the weights that is shown at the end between your reservoir outputs and the target values. Okay. So compared to a typical deep learning network of similar size, the number of weights that you have to learn is far, far lesser. Okay. So which means that the training that you will have to do is much more tractable in this case compared to a typical deep learning scenario. So the quantum reservoir computing is all about replacing those reservoir nodes of classical dynamical systems by quantum dynamical systems. Now you remove all your maybe classical harmonic oscillator, etc., and put in quantum dynamical systems. So what we have been doing is to put in what are called quantum chaotic systems there. So we have a collection of quantum chaotic systems which are simple maps. It could be what are called kicked rotators or kicked tops and so on. And they will do the learning task for us. And the advantage, as I said, is lightweight training. The number of weights that you need to determine is far fewer. And one useful thing is that the quantum reservoir computing does not require a gate-based quantum computer. In fact, we are realizing one version of this quantum reservoir computer in a NMR system with my colleague T.S. Mahesh. I'll show you just one experimental result here. So this is a regression task. And the prediction from the training data is shown in that orange color, and the stars are the prediction from test data. So it has a very good agreement. So this is something that we've been working on, and this one is a classification task where we are looking at states and checking whether it's entangled or not. Again, reasonable this one. Due to lack of time, let me not say much about this at this point. So till now I have been talking about what are the promises of quantum machine learning. So in this slide, let me talk about the gaps part of the quantum machine learning. One of the biggest challenges is that encoding large data sets is a major challenge. Today the classical machine learning paradigm is kind of in such an advanced state and developing on a day-to-day basis to an extent that trying to confront it with the quantum paradigm is increasingly challenging simply because of volume of data that the classical machine learning paradigm can handle. Okay. So we are at a point where we need to put in a lot more effort into how to encode classical data into quantum data. There are already existing algorithms for it. For instance, one popular algorithm is called a QRAM, quantum random access memory. Unfortunately, it has not been able to experimentally implement it in the last 10 years or maybe 15 years since the algorithm came out. There has been not a single implementation of it. But it's a promising algorithm. So all these are questions that are still things that require considerable amount of research. Which also means that you need to do very efficient state preparation for quantum machine learning purposes. And second point is about non-availability of curated quantum data sets. I think anyone working in typical machine learning would know that there are these data sets that are available. So if you come up with the algorithm, you can use those data sets, check if your algorithm is working well and so on. So I think there are one or two available, but not sufficiently in good number. That is again something that is really required to move the field forward. And another theoretical challenge is to determine appropriate loss functions. And there are some problems which are common between classical machine learning and quantum machine learning, which is like this Baron-Platten issues, which happens in many neural networks. It also happens in quantum neural networks. And there are effects of hardware noise which are not accounted for. This is something very important. In the sense that I talked about these algorithms, HHL algorithm or quantum support vector machine. In these algorithms, we have not accounted for how long, what is the effort that is required to encode the data into quantum states before these algorithms can start their work on it. Okay. So if suppose that is going to actually take so much time as to kill any advantage that comes from the algorithm itself, then our purpose is defeated. Okay. So the current hope is that this loading the data, encoding and loading the data can be done in linear time. Okay. So that's the best case scenario if that can be realized. And again, that's a question of intensive current research, and that is something where we need to put in a lot of efforts. And there are other issues like error corrections and decoherence, but these are not specific to quantum machine learning. These are issues with quantum computers and in general any quantum systems as well. Okay, I think I'll stop here at this point, and thanks for your attention. I think Sandeep has a question.
So thanks a lot for a great talk. So just to ask you about that example where you were talking about quantum machine learning and you had that quantum chaotic system in the middle.
This one?
Yeah, this, the previous slide, I think.
Yeah.
Okay.
This one, is it?
Yeah.
Anyway, it's a schematic.
Yeah. But why, I couldn't understand why is it so much more efficient than, a standard machine learning?
Okay, so one thing, so there are different reasons. One is like when I put nonlinear chaotic elements here, you also take advantage of the nonlinearity in, so typically as you can see even in this figure, the input is imprinted only on those 3 qubits, okay? And they need to be efficiently propagated through other qubits. That happens much faster when you put in nonlinear chaotic elements compared to just putting neural networks. So in some sense, the imprint travels much faster simply because they are chaotic. And another reason is that because now let's say you put in n of these quantum reservoir nodes, the space is now much larger. And let's say that the hope is that similar input data will go to similar corners of your large Hilbert space. So any problem like classification and all is relatively easier to do.
I mean, if it were just the chaotic part, one might ask if you had a classical chaotic system, would that be?
Yeah, sure, that works. Yeah, so there are, I only spoke of quantum reservoir computing, but there is a classical reservoir computing where, as I said, you can remove this and put things like logistic map or any other chaotic element like Lorentz model and so on. They work equally well. And that has been like many papers are there on that.
Sorry, I don't know the field.
Yeah.
That's as good as the quantum? Or
no, so this one I think will also have an additional advantage of the fact that the Hilbert space is large. So when you want to do especially classification and similar problems, this is far more advantageous.
Okay. Thank you.
Thank you for the talk, sir. It was really interesting to know. My first question is the time complexity that we talk about. Does the time complexity written in a particular example specifically factor in the error correction algorithm time complexity as well?
No. These ones don't factor in those.
Okay, so despite adding time complexity of the error correction algorithms, we still see a significant difference?
No, we don't know. All these have been demonstrated as a proof of concept that these algorithms work. And so there are many papers which demonstrate these algorithms. So now we know that these algorithms work in practice in a real experimental setting. Now to really check that, what you are asking, like error correction and everything, I think you need to do the problem on a larger scale, and that has not happened yet.
Another question, I don't understand much about architectures, but when I talk about machine learning, I think of an AI model. Artificial intelligence is one word that comes up. So talking about artificial intelligence model, AI model, based on a quantum machine learning thing, let's take an example of a classical machine learning model based on some neural network architecture. So what is the quantum mechanical analogy or an equivalent to the same that exists today that can be talked about? The architecture.
Okay, so I think if you're asking like you constructed a AI model putting together neural networks. Yeah, so there are quantum versions of neural networks if you want a precise analogy. But in that sense, some of these things like even reservoir computing and things like that, they are not precise analogy. They are analogy only in the sense that same class of problems can be solved using this. There is no reason for us to stick to one way of solution. Okay? It works for you in the classical sense, but what you need to do is to say that, no, I have this problem, I want to get it solved. Whether it is done by using neural networks or by some other means is not your problem. Why should I prefer one method over the other? I would actually prefer one method over the other, provided one of them is doing it efficiently, like far more faster, then there is a reason to prefer, but not because I like neural networks.
And just one more last query. On the slide of time complexity, if you could go where you have given example of two variables, an equation, this one. Here, when the HHL algorithm is mentioned, there is a constant k square. Is it just a mathematical constant, or what does k signify?
No. So k square is what is called a condition number of a matrix.
Okay.
So condition number basically tells you how, what is the stability of that matrix, in the sense that if you perturb the matrix, how are its eigenvalues going to change, for instance? Is it going to see a huge change or only a small change? Okay. So it's a number that is, there's a precise definition for it. I don't have a board to write it, but we can talk about it later. But it's essentially an indicator of how stable the matrix is to small perturbations.
Oh, okay, got it. Thank you very much.
Hello, sir. How eigenvalue and eigenvector help in quantum machine learning?
Okay, that's a broad question in the sense that, see, a lot, I mean, not just in quantum machine learning, in all of quantum computing as well, I think most of these things depend on eigenvalues and eigenvectors of either a unitary matrix or a Hamiltonian matrix. So without computing the spectra or without knowing the eigenvectors, you won't be able to, say, construct the algorithms, or you won't be able to make sense out of a given matrix. So they kind of tell you in some graded sense what is the information content of your matrix. So in that sense, I think these are important. So for a quantum system, eigenvalues are simply, they could be the mean values of some operator. If it's Hamiltonian, they indicate the energy, for example, the possible energies of the operator. And if it is some unitary matrix, they are what would be called the eigenphases. So they are certainly very basic quantities one needs to work with, irrespective of whether we are working in quantum machine learning or not. Even if you start off with quantum physics, you need all that. Yeah.
Okay, thank you, sir.
So you showed the, it's a brilliant talk, thank you, sir. So you showed the classical classification problem, that graph from Wikipedia. I just
this
want,
one?
The classification problem.
Yeah, right.
So just wanted to ask, what would be the quantum analogous picture of this, and how would like the variables look like?
So see, it's same. It's not different because your problem is the same. The classical data is the same. You want to classify, that's your problem, and that doesn't change. That's because you're using a quantum algorithm. So the only thing that changes is the algorithm, how you're going to maximize the distance between the blue points and the green points. So as a schematic of the problem, it is exactly the same. That doesn't change.
And does it help using a quantum?
Yeah, that's right. In fact, that is what this tells you. So your classical SVM solution to that takes order of m square into m plus n, whereas quantum SVM is logarithm in m into n. So it gives you an exponential advantage, at least in theory, yes.
Thank you, sir.
Thanks.
Hello. So the barren plateau problem that you talked about, so in quantum case, it's as bad as classical, or is it slightly better?
Okay, I don't know enough to make very detailed comments about it. And also, more importantly, I don't know how serious the barren plateau problem in the classical neural networks is, because I have not actually worked on that. But it is serious enough to merit lots of papers being written on it.
Yeah,
that is the only comment I can say.
Yeah, this is a question in a general context. See, when we, since we are dealing with the computational time whenever we talk about quantum computing, and the approach to solve a problem, that is going to be very critical when we talk about the time taken for solving any general problem. So there are there are complex problems which can be solved in fraction of seconds if we change the approach. For example, what I have in mind is that certain optimization problem. So you can solve it pretty quickly, say if you adapt to a geometric solution. So is there a way of thinking about it, like how do we bring in geometric solution kind of approach to to reduce computational time very significantly? Is there any way of thinking about it?
See, one thing that can be said is the entire framework of quantum mechanics itself is very geometric. All of this you can think of, all of whether it is quantum computing or quantum machine learning, qubit is a point in a Hilbert space, in a large Hilbert space, and everything is about cleverly rotating these qubits and measuring it. So if you want to take that geometric approach, you can always do that even with existing algorithms. If you think that that helps you do it, you can forget all this mathematics. Think of it as clever rotations in a large Hilbert space and work with that picture. But it's not very clear to me that just changing the picture from this mathematics to geometry will enhance the speed in itself. Because you're doing the same thing. It's just two different ways of looking at the same thing. Unless you mean something different. Yeah.
Okay, we can talk later. Thank you very much.
Thank you so much, sir, for shedding light on quantum machine learning. Now I would like to invite Professor Manoj Dhambir for his talk on quantum computing in practice, what works, what doesn't, and what to learn now.
Good afternoon, everybody. Thank you for the introduction. Just one correction, I am no professor, so just not much in academia. I'm still a student, actually, if you realize, but that's okay, we'll keep it for later. Nevertheless, let me talk about, I'll give you an industrial perspective. Okay, so that's something I'll start. So many of it is non-quantum, but bear with me because it's important to have that perspective as we, move into quantum also. So you need to see how quantum fits into the space of things that happen, right? So let's start with that. I'll I'll be skipping slides because I'm sure we don't have a lot of time. But nevertheless, let me start with the background talk, right? So here, so what we can see is that this is a bit about TCS, okay? The company I work for represent, right? So we are in the business of building, designing, and maintaining applications for our enterprise customers. Enterprise customers, anyway, enterprise, large enterprises or companies, you call it, they're businesses, right? TCS is more like a B2B company. We don't have retail customers. We just cater to businesses or companies. And our job is to help build computing systems for them, okay? Either do it on the cloud or on their private data center, make sure that it runs well. So we'll talk more about that. And most importantly about these computing or application systems that many of these companies run in their software. Today, every company depends on it so much, okay, because the way you run those applications or your software actually influences how competitive you are in the industry, or how much profits you make and how much revenue and so on and so forth, right? So that's one thing that we need to understand here, right? And most of these systems, I mean, almost, I would say most, all of these systems are large-scale systems. And large scale means what? Lots of code, lots of hardware, lots of networking, lots of users using it, right? Lots of data, lots of things, everything, lots, right? So I'll give you an idea of what these systems are, right? So you can get, I mean, this is actually a very old list. Today, the kind of applications have grown quite a bit, but this gives you some idea of what this large is all about, right? And of course, one thing you have to remember is, although people may talk about AI killing most of it, but you still need lots of large engineering teams, okay, to maintain, build, and run this software, because very high stakes thing, right? It's kind of the lifeline of a company. If that system goes down, they stop making money, they stop making business, everything. Yes, right? So let's go on with it. Now, what do we want these systems to be capable of, apart from the functionality, right? I mean, all these systems are tested for their functionality before they are actually deployed to run for real users, right? So these are some very important things that we want, okay? And you may think why we are talking in a talk of, even in a quantum discussion we are having this, because quantum is also there to help some of these things, right? And all of it actually, right? So, I mean, sometimes, yes, students find difficult to even, put these things in words, but they're very simple actually, right? Latency means runtime, okay, T2 minus T1, the standard. Throughput means amount of work you can do in a given second, right? And of course, there are a lot of things that I'd like to point out, the precision quality, especially in a discussion on quantum, right? It's important. The solution quality becomes very, very important, and the importance of it is highlighted when it comes to quantum as well. Lastly, yes, energy. Anything that you want to do, you want it to do it with low energy and low cost. Everything is important, okay? In order to have something, you need to have a good combination of these parameters for an application to be deployed in the industry. Otherwise, it doesn't work, right? So, and also end-to-end. I mean, we are not talking about just this part algorithm or that algorithm or this part of an application, no. We are talking about all these characteristics end-to-end. End-to-end meaning from input to the output. I mean, otherwise an application can be broken up into many components and you can say each of them have an input and output. No, we are talking about everything for the entire application. So that's the idea here, right? And let's take a holistic view of this whole thing. Most people, I mean, you'd speak of, right, think of performance, I mean, all these things which I presented on the other slide is dependent totally on the infrastructure or the hardware, right? It's not just that. I mean, a lot of it depends on application, the kind of application that you're running, and also what we call the workload. I mean, we will open up on what workloads are in the next slide. Let me get into that. But what I want to bring about is that it's all these factors that together contribute the performance or these key performance indicators which I listed in the earlier slide. So let's talk about application types. Okay, there are two types of applications, right? One is interactive. Interactive means, you know, somebody is interacting with the application and he expects the response like quick or real time. Or there are, like for example, a human interacting with a computing system or some control system, so to say, right? I mean, certain things have to happen in real time to control some manufacturing or some process. So that's one kind of application where that latency is very important. And the other kinds of applications are large jobs. Okay, like I think Professor Santanam also spoke about it, right? Whether it takes for minutes, hours, and days, it takes that long a time to run those things. So you can get a feel of where quantum fits in, right? I mean, I wouldn't think of it for running interactive applications, at least not in the immediate future, but definitely the batch reports or all these things are part of simulation modeling kind of problems, which take a long time to run. And they are, you can think of some of them can be intractable. And those are what we expect quantum computers to target, right? And on the other side, I'm talking about workload characteristics. I said application type and workload, right? So the workload, of course, what characterizes the workload depends upon the type of application, okay, and the number of inputs, you know, the kind of data you have to deal with. Okay, if you have a database, that means, and if you have a 10 terabyte data, then that's another part of what you're dealing with. It affects performance, okay. Concurrency, how many users are actually using your application or running jobs? Okay, if you have more jobs running, if you have more users accessing your application, that contributes to the definition of a workload, right? And of course, others, depending upon the kind of nature of the application that you're trying to solve, you can talk about workload in those domain-specific terms, right? Like for example, if I'm solving an optimization problem, right? I mean, how many variables are you trying to optimize? How many constraints do you have? So those kind of things. If you're trying to discover molecular properties, people talk about how many atoms, right? So in many ways you can describe what a workload is, but the point is it is these factors that affect these performance indicators of an application, or of a system, right, or a computing system. Now, there's one thing I wanted to bring about in terms of quality. We spoke about quality as one of the factors. And that is very important. In certain cases, you know, accuracy, for example, take accuracy, right? Accuracy is a given. I mean, take a banking application. If I give you 10 rupees, your account, my account is debited 10 rupees, the other person whom you're giving to has an increment of 10 rupees, you need to have perfect accuracy. You cannot have any random number being debited and credited. So there are certain applications, you know, you need that kind of accuracy, and there's no going away from it. But there are many other kind of applications which don't really need. Okay, these could be kind of supporting applications or helping applications where you know that, okay, 99% of the time I'm doing well, it's okay, right? And that's one thing. The other thing is, you know, in certain cases, accuracy becomes very crucial, especially what we have seen in chemistry and those kind of domains. They actually look for accuracies in millihartry levels, and that also sometimes you count the decimal places, 4 or 5 decimal places, sometimes it becomes very, very difficult to achieve, because so much that we have to use 64-bit kind of computing to actually achieve that. Now, if you look at it,
even this is not so absolutely big requirement as in banking, but the more accurate you are, you can save more costs. So in one case, it's like a constraint, and in another case, it's more like an objective to minimize. So even in these performance indicators that we've spoken about, right, some of them are like hard constraints. I want my response time in response in 2 seconds, means that's a hard constraint. But in some cases, you can say, okay, try to minimize it as much as possible. That's also good enough, right? So that's one thing which I wanted to talk about. And why I'm talking about these things, because this is also impacting the workload. Okay, if I need high accuracy, then I obviously need to involve a lot of complex math operations and correlations, interactions, which I wouldn't otherwise do, right? And the other thing is optimality. Optimality also is a very important thing in the sense that and it's common that many of the times in the industry that when we try to solve an optimization problem, it's not always essential that you get the absolute minima of anything. I mean, if you're trying to minimize your cost, even a reasonable reduction in cost is pretty good. And I've heard people talking about where even a 1% reduction in the cost can mean like millions of dollars or even $10 million and things like that. So it's a big thing to even bring down the objective, small changes essentially. So that's about optimality, which I want to talk about. And now we will come to intractable computation. I will not spend too much time on this slide. I mean, in fact, I don't need to spend any time on this slide. Professor Santanam covered it very nicely. So, we all know about exponential complexity, polynomial complexity now, and where we want to target quantum computers. Essentially, what we say intractable is the exponential complex ones. And those are the kinds where you want to use quantum computers. But nevertheless, it's also about the problem size, because not everything needs to be exponentially complex. There are certain things which the problem size is much larger simply because the size of the workload or simply about the size of the problem. So even those cases, you can use quantum computers to solve problems. So that's one thing which I want to bring about here. Now, from our end, from TCS, there are 3 areas of focus. Of course, we look at it from the applications perspective. So looking at the applications we target for use with quantum computing, these are chemistry, quantum chemistry, optimization, and of course, we are also doing explorations with machine learning. So that's the basic thing. Not, especially with machine learning, it's not much about the theory, but results are interesting. Even the empirical results, you can see that, we are getting interesting results, and that's what keeps us going by exploring quantum computing here. So, okay, let me skip this slide. I'll just move on. I'll just talk about the various optimization problems or various use cases that we have been worked on. So this is about, part of it is machine learning about, we've used it for segmentation kind of work. We've used it for, variational algorithms for drug discovery, right? Optimizing the postal delivery, right? And in the bank for doing crypto work. Of course, this is more of PQC, but yeah, I mean, it's just to give what we are up to. Right, and capacity planning, this is more of a optimization problem. Unit commitment is actually a energy management problem where you want to make sure that you're generating as much energy to meet the demand, because sometimes energy management is what I understand is a very hard problem. Essentially, many a times, given the dynamic nature of energy requirements, energy companies tend to generate more energy, and that results into a massive waste. And hence, it is essential that you align your resources in such a way that you meet the demand. And a little bit of demand forecasting is there. And while there is a demand forecasting, you also try to look at, you have so many sources of generation of energy, and you want to optimize in such a way that your energy cost of generation is low. So of course, I don't want to talk about each and everything. But nevertheless, the idea is that, of course, we are aware that the NISQ regime of quantum computing is going to continue for a long time. NISQ means noisy computing. We are not expecting fault-tolerant hardware to come anytime soon. Okay, so as a result, we try to work on hybrid algorithms as much as possible. So that's one thing that we do, and we try to be resource efficient. So we'll see a few case studies in that along with the thing. So challenges, right? So some of the challenges we face when we work on quantum algorithms, use quantum hardware on the cloud, so on and so forth. So that's to do with one of the main things I spoke about, cost, right? So now pricing is a big deal. I don't know how many of you tried to access quantum computing resources on the cloud, but if you look at those costs, right, you may see that they are less than $1. Those numbers look very small, but when you're trying to run an experiment, okay, it can go into hundreds and thousands of dollars, because you will have that many number of circuits to run, you have that many number of samples to take, okay, and money is really hard to come by. I mean, does it make sense to run an entire quantum algorithm on the cloud by paying so much money, right? So that's a big deal, right? And this can continue even when you have fault-tolerant quantum computers. I mean, don't expect the price of quantum computing to come down all of a sudden, right? The other aspect is of course, I see this as a bigger problem, that is converting the language of optimization, because in TCS, optimization is not like, started yesterday. They've been doing it for decades now. And most of the time, people like to encode problems in what they call in ILP kind of formulation techniques. So what you do is I'm assuming many of you understand what ILP is. So what I have here, I think my mouse is not, okay. On the right side, upper side, you see those linear kind of equations. Those are like ILP formulations, right? So you have a linear objective function, then you have inequality constraints, you have equality constraints, you pass it, and what you have is an ILP formulation. But nowadays, when we are looking at feasible quantum computing, I mean, not about the HHL, I mean, it's infeasible, but all the other variational optimization algorithms like QA and all, they are all something that we need to run in a QUBO format or a quadratic unconstrained binary format. So which means that you have to now optimize binary variables as opposed to what were integer variables or continuous variables. So that's a different problem actually. And what we realized is that when you convert from that formulation, the linear formulation, to the Ising formulation, there is a loss in translation. I mean, you won't see this kind of a problem when you're converting a software program from C to Java or Java to Python or so on and so forth, right? But here, the language conversion effects are irreparable, because what happens is if I convert this problem statement, the ILP problem statement, to a QUBO problem statement, I still have to make a decision on how to apply penalty weights to various constraints so that I get the correct solution. But usually what happens is, I mean, this is not even a quantum problem. Even if I use something like a simulated annealing for that matter, right? You will see that constraints are broken. I mean, that doesn't happen when I solve an optimization problem using a Gurobi solver or a Cplex solver, right, which is commonly used in the industry, right? But if I'm using a QUBO solver, I see that my constraints are broken simply because I am not able to decide on what are the correct penalty values I need to give to my constraints. And this I see as a very big problem, even though it's not related to quantum computing. Okay, so that's very important, and until quantum algorithm is really coming about that can solve this problem, or if we have fault tolerant, I mean, we're not going to be able to solve this for a long time.
The other part, of course, is mitigating errors. Okay, that's a lot of overhead there. I'll give you some cases on what we have done. And then lastly, right, validation or verification. I mean, this is a fundamental problem in sense that you have a quantum simulator, you can see some results. You can verify it on the quantum hardware and you can see, okay, the ratio is 1.9 or 1 is to 2.75 because you have been able to verify it on a simulator. You are able to verify what the result of the quantum program is. Now, if I have to do very large problems, let's see, we already have 158 qubit quantum computers. Okay, we may not be able to run a simulation or run those programs on a simulator. Now, in such a situation, how do you know whether the result that is coming out of that computer, okay, is a really good, correct result or not? Because you don't know how to verify it. Okay, if I had a quantum simulator, I could have done it, but that will work only for 45 qubits, right? But I cannot go overboard trying to figure out. So that's a big problem. How are you certain about these things, right? So let me, before I get into prescriptive mode, let me just talk about some of the papers that we have published. So one is zeroth order optimization. So zeroth order optimization is about a variant of gradient descent where you have second order gradient descent where you look at the second order, where you take second order derivatives into the gradient descent. First order is the standard gradient descent. And zeroth order is essentially no calculation of gradients, but just taking a few random points in a short unit sphere of where your current solution is. And what we found was this actually works for us. And it works for us in such a way that we are able to save lots of money. Because think about it, if I use my standard gradient descent, it takes so much time to converge, okay, and this is boiling down to some thousands of dollars here, but when I'm getting a much better gradient descent using my method, I'm able to run it. Of course, these are all empirical measurements, I mean, and we are also building rigorous proofs of convergence and the number of iterations and all that. I mean, the papers are being published as we speak, but this just to give you an idea of how certain methods can help you, reduce costs in the when you're using these resources on the cloud, right? And even otherwise, right? This is, of course, topological data analysis. I don't know what Bernard spoke about, but this is looking at data in a topological format. So it's like saying you lay out your data in the three-dimensional space or in a hyperdimensional space, count the number of holes, and it tells you something about your data. So you can learn interesting things about your data in a certain way. Now here what we did was we used topological data on simple images. And as a case study, we trained a machine learning model to detect the Betty number. In this case, it's called Betty number. Betty number is called the number of holes in your topological data. And we used a quantum machine learning model to actually generate the Betty numbers and do some inference over it. And that is what we have presented in this paper. This is just to give an idea of how, and here also you're able to, compared to a classical machine learning model, you're able to, in quantum, you're able to train this with much lesser number of parameters. So that's the other thing. Okay, this is one algorithm which we did with an intern. Actually, it was from IISER Pune, I think. Right? Yeah. So that's the where we came up with the method of reducing the complexity of a tensor SVD algorithm. So this was one of the things. I think it's been about a year now, more than a year now. So actually, I have a dated slide deck, but nevertheless. So the other case study I wanted to give about is use of parallelized ansatz. Now in parallelized ansatz, what it means is I have a circuit where I can apply gate operations in parallel. Like if I have many independent pairs of qubits, I could apply gate operations on them. And this gives me
the benefit of reducing the circuit size very much compared to what could be like a well-known UCCSD ansatz. I mean, don't worry so much about these names. It's very difficult for me to explain those terms here, but understand that standard VQE computations for computing molecular ground state properties, it's a very high depth ansatz, which means it's a very high depth circuit. Okay, but using certain ansatz which uses parallel gate operations, okay, my circuit depth is reduced quite a bit. And as a result, what I'm able to do is I'm able to simulate these things much better on real hardware compared to the other ansatzes. So that's the main study here. The other thing we also do is to, of course, in this work, what we have done is we have also done some work in machine learning in trying to predict the correct initial state. See, if you look at the gradient descent, right, I mean, all about how many iterations it takes to run, right, your quantum circuit. So if you can guess correctly, you know, you're already way down there. So there was a machine learning model trained for doing that. At the same time, there was another machine learning model that was trained to correct the results that were coming from quantum circuit measurements, and that together really gave good results. Okay, now here is another work where machine learning has been used in the area of quantum chemistry to reducing the state or the state description. So I don't know if you're familiar with variational autoencoders, which are typical in machine learning. What it helps you do is it takes you take a big input and compress it to a very small representation without much loss of data. And that is what we did. And good thing for us is this is a very good idea for noisy quantum hardware, because if you use a full state and run a VQE on it, okay, just because you have a large circuit depth and large number of qubits, you are prone to much more errors. But if you use auto-encoded state, okay, and run the VQE on it, we realize that we are able to do it with much lesser number of iterations, and we are able to get much better accuracy on a real hardware. So these are like, I don't know, some cheat tricks. Okay, we need to see how we can make it more generalized. That's the challenge. But some cheat techniques to try and see what we get, right? But they are interesting enough that conferences like to publish these things. So that's a good thing for us. So yeah, this was about quantum chemistry calculations. 1 second, I think I already covered this. Let me. Yeah, this is about the. Sorry, this was about this is an illustrative diagram about reducing the Hamiltonian size and everything, and getting the same chemical accuracy compared to a larger one. So that's this. Now I'll talk about. See, we have now access to the real quantum computing hardware because we have access. And I'll tell you some experiences with error mitigation. This again is a study with. 1 second, have I done this right? Yeah. So you can see what we have done here is that we are trying to use various ansatzes to solve a VQE problem. Now we are not running the entire VQE simulation, because even for one circuit we are trying to study how we can do error mitigation to minimize the errors. Okay, so we are not running through the full VQE, but just doing one circuit thing. And of course, I'll not get into all kinds of error mitigation, but there are certain times when error mitigation can introduce more error than without mitigation, as you can see here. Okay, and one of the things we have seen is that even this graph is variable with time. So essentially, even by running the experiment, we don't really know what the effect of the mitigation techniques are. But one thing is for sure, is that zero noise extrapolation is the error mitigation technique that outperforms all. And this is about systematically adding noise into the circuit in such a way that, so you kind of regress over it. In some sense, you add 10x more noise, 5x more noise, finally 2x more noise, so much that if the noise was 0, you simply regress over the errors and you get a reasonably good error estimate or the correction of your quantum circuit, right? And this is all done. The good thing is this can be done across any kind of quantum hardware. It is not just limited to IBM Q. It can be done on ion traps, because all this, most of the work is being done by modifying quantum circuits and adding a little bit more overhead. So, of course, what happens is when you're running zero noise exploration and all, there is a lot of runtime, because the number of circuits you have to run is at least, as much as you're running, taking samples for collecting your regression data, right? So you can think about, almost forget what advantage is all about. But at least you know how to get good results from them. And of course, as part of our exploration efforts, what we're trying to do is, can we reduce the number of samples to take so that we can, predict the correct results as much as possible. Now this is similar circuit, we are just doing it with a different ansatz. But now you see, when you do it with a different ansatz, the graph is very different from how it is for another ansatz. So, you don't really learn much by running just one circuit. So essentially it is important for us to create so many circuits and take a lot of samples if you want to even think about creating a machine learning model that can mitigate some of these errors, or determining how many error mitigation runs to run. Because error mitigation also, what you see on the x-axis is just 4, but in reality, if you look at so much parameters that these mitigation techniques have, you can easily run more than 100 experiments for exploring all the error mitigation possibilities, right? So that's the thing. So this is just to say that. And also sometimes, you have to see how this error mitigation works as a function of time, because sometimes, you recalibrate a certain hardware and, at time t is equal to 0, or at time t is equal to x, what is the error mitigation behavior? After 2x, what is the error mitigation behavior? Because otherwise, you never know what how to control these things, right? So that's important, right? Now the other thing I wanted to talk about was quantum resource estimation. Now quantum resource estimation is a important field, because these are the days where everybody is asking about when will we get quantum advantage, right? And if you want to be able to say when you're going to reach quantum advantage, you should be able to know how much time I'm able to run my classical algorithms on classical hardware, as opposed to how much time it takes to run on a quantum hardware. I need to be able to compare. How will I do that? Okay, so resource estimation is one such field of study where you try to estimate what is the quantum runtime of my algorithm. Right now, if you look at these slides, it should not be coming as a surprise to you. I don't want to go through each of them, but all these things, number of gates per second, number of iterations you have to run, number of shots you have to take, right? All these add to the real runtime. No matter what your theory person will tell you, O of n square, there is much more to be done when you're actually running on a real quantum hardware. Okay, a lot of these things, add to it the error correction overhead, error mitigation overhead. IBM Q doesn't have error correction, but that doesn't stop you from designing your own error correction circuit if you want, because you can still use their qubits to do error correction if you want to add that, right? So many things are there. And what come about is there is a very nice tool called a Microsoft Quantum Resource Estimator. Sorry, I didn't put that in there. It will tell you, for your given quantum program and problem size, it will tell you how many qubits you need, how many of them are algorithmic qubits that are there in the brown part of the pie graph, as opposed to the correcting qubits like T flops, T gates, and everything. So that's one aspect of it. The other thing it will tell you is what is your runtime. Okay, it will tell you what the runtime of that circuit is given your circuit description. So that's one thing that is really good about this quantum Microsoft. So you search on Microsoft Quantum Resource Estimator, and it's available in GitHub. You can download it and play around with it, and it takes into account all kinds of overhead. What is my error correction overhead? Of course, error mitigation overhead is not something that it takes, but you can definitely look at it, because mitigation is essentially a classical algorithm, but with a few tweaks, which you can actually include in this circuit and, still get to know what the resource estimation or runtime is. And doing this and comparing with your classical application is what will give you what is the time it takes, and you can compare when you get the advantage, right? So very, very useful it will be when it comes to evaluating various things. Now, of course, lastly, I wanted to touch upon this topic as to how will you know that the answer is correct, okay? And that depends upon the kind of problem you're trying to solve, right? If you're trying to solve an optimization problem, okay, if your quantum algorithm is giving you a number that is better than what your classical solver is, because mind you, you can easily verify the optimality of these numbers that you get, right? And you can easily verify that, right? And in chemistry, okay, you can do it with experiments. If you have experimental data, you have published numbers, you can verify with those published numbers to see, hey, is my quantum circuit giving me correct numbers, right? And likewise in finance, because most of these cases, data is already available. But what when you don't have data, especially in a case where I'm trying to discover a new drug or a new molecule or a new material, if I don't have data, how do I verify? How do I know that my answer is correct? Because there is no way for me to verify it classically, and I cannot run my quantum program on a simulator like we are very used to doing it. But that's the big problem. But it so happens that in 2018 there was a PhD student who came up with Uma Mahadev, who actually came up with a protocol. So her work showed that it is possible to verify or check if the answer is correct, okay, based on just classical software. Using classical algorithms, you can actually verify whether the answer is correct or not. But it's, again, not without its overhead, right? I mean, sometimes you have to, your depth increases 100 times, your number of qubits you need increases 100 times, 40 times, and you need to run more experiments. But at least, there is some method that says that you can classically verify it, though still, in today's terms, it is still impractical. So we need to still really think about how we can make these kind of methods more practical, because when it comes to the industry, it's not an easy adoption, right? Although we would like to be very sure about what answers are coming out of the quantum circuit, right? So that's that. Now, apart from this, let me talk about classical work that we've been doing. So just wanted to showcase here is that we have built some classical software that can compute properties, material properties, much better than certain industry standard softwares like Orca and other things. Like, we can do it 10 times more faster because of the, it's of course the answer lies in all the linear algebra and implementing techniques like downfolding, which can do coupled cluster interactions and so on and so forth. And as a result, we are able to do it 10, and this is, if I'm able to do it 10 times faster, means the big thing in the industry is that it means that my drug discovery times or material discovery times is much faster than otherwise, it takes years, and all the bottleneck is because of the computing. And if we are able to do this with 10 times less time, it's much better for us. It's just that we need a lot more GPUs, but it's scalable. So that's one thing which I want to bring out. And this is something that is possible even using the method. We are able to show that even our quantum circuit depth is many orders of magnitude much lesser. But it is still not in the practical regime because these algorithms require a fault-tolerant computer. But nevertheless, we are looking at ways on how to decompose this problem and run it as independent quantum circuits and combine the answers. That will hold some promise going ahead. So that's basically what I want to talk about. So summarizing, of course, this is not everything that's said, right? I mean, so if you want to do something useful with quantum computers, I mean, try to come up with short depth quantum circuits, learn error mitigation, try various combinations of error mitigation, right? Try to look at gradient descent methods which converge faster, right? And of course, I mean, I didn't give a case study, but definitely think about how you can pack as much gate operations in parallel, so on and so forth, right? Decomposing, combining, everything, right? So we have seen other things. Verification is a problem. Converting problems from ILP to QUBO is a problem. We need to really do more research on how we can overcome those problems, right? And the large resource requirement which we'll need to deal with for quite some time. And in terms of learning, I just thought I'll put a few pointers, like using quantum resource estimator, right? That will be one thing. Learn error mitigation correction, because these things are going to be very industrially relevant, as if some of you are interested in moving into the industry and do some serious quantum work. That is very important. And also, last but not the least, I will say, take use cases and see how you can apply it to optimization and machine learning problems using quantum algorithms. That will come in very handy. And lastly, I would say, it's not just about universal gate model quantum computers. There are other hardwares that are like D-Wave is there, Pascal is there. Now, the Pascal is a very interesting capability it has, is that it can help you. It's an analog quantum computer, but it can help you optimize your QUBO problems by helping you modify the schedule. Okay, and there are a lot of more classes of problems you can solve with it. I'll definitely encourage you to explore those things. And there is, while we speak, I mean, most of what we say, qubits and everything are all digital quantum. Nowadays, there are new quantum paradigms coming. They are called continuous variable paradigms, where instead of qubits, you work with modes. And those modes are nothing but probability distributions in themselves. And there are some interesting algorithms coming up in that regime as well. So, I mean, it's worth looking up. So it's good to be open about trying to learn as many quantum hardwares that are there, trying to be as open as possible, because today we don't know what kind of hardware or what paradigm is really going to be successful in the industry. So it's good to have some breadth and of course depth also. It's all useful. So that's basically it, and I'll stop my talk now. Thank you very much. If you have any questions, please feel free to ask.
Hi, Manoj. Interesting. So one of the optimization problem, what in our daily experience, what works magically well is this Google Map. And we, starting point, given the chaotic, traffic in Mumbai, it precisely magically predicts the reaching time. So what do you think? What is actually going on? Can you say something? What exactly
actually,
is?
This is something which even I am amazed with. Okay, I don't have the answer to it. Okay, what they must be doing internally, I'm not very sure. But I'm sure there will be some interesting graphs of search problems which run with very low complexity. Or there must be some approximations where they are not very obsessed with having a real correct answer, but something that really works most of the time. And probably that's what I think is making it tick.
Sure, thanks.
Okay.
Just a quick question. Sorry to interrupt. I just had two quick questions. So the first question was... Okay, I'll just ask one, just to speed up. So it was related to the gradient descent implementation that you had presented, the 0th order one. So in typical, the limitations associated with gradient descent are that it's not able to handle saddle points and it gets stuck in local minima often. So the advantage that's being offered in the 0th order one, is that more of from a speed up point of view, or is it more of finding the global minima efficiently?
It's more about finding the minima efficiently.
Okay.
Okay, so
See, now we need to still, we are now working out theoretical guarantees on as it works. Now, what this was done was it just took a few problems and implemented it. And it's like, we like to see this work. So we have some theoretical guarantees, so that is, papers are accepted. So they will be actually, this is getting published in SIAM actually, so it will be in May, it will get published. So that's
Just one small short question. So this is typical from a finance point of view. So I just wanted to ask, with respect to the quantum boom and speed up that we're getting offered, is there a big limitation to utilizing traditional techniques like value at risk, let's say, or even other risk-based metrics in finance?
See, these algorithms, value at risk and all, very well implemented, using classical techniques. And they are not that, I would say in my view, exponentially complex to really attempt on a quantum computer. Of course, we may come up with some algorithms, I'm not saying no, you may come up with some algorithms that can do better, faster, but at least not at this point, there won't be that much interest. But say if you want to do something like a portfolio optimization, then yes. I mean, these are all harder problems compared to a value at risk.
Good evening, sir. So basically, as you mentioned, portfolio optimization, that is exactly what you are working on right now. So when we are dealing with medium-sized assets, so we are looking upwards of 50. So we are facing limitations in the sense that runtime is larger and converting qubit to the Ising form, you mentioned that there are like translation errors. So how do we go about either mitigating them or maybe the approach is not right? How?
Well, I will first suggest that you tune your penalty parameters, at least they work with classical solvers. So you get your penalty parameters right. And then you can try to jump into quantum implementation.
Okay, sir. Okay.
Right?
Yeah. Thank you.
You will have to tune them. You'll have to try various things, and because that itself is an optimization problem to search for the right kind of penalty parameters. But people try to do some grid search over it. Sometimes some people have some intuitive idea of what it should be.
So is there like is it like a trial and error, or is there
people do it trial and error?
Okay.
Yeah.
Okay. Thank you.
All right. Thank you. It's been nice talking to you all. Thank you.
Thank you so much, sir, for giving the sense of how quantum is there in the industry, like the state of the art of the industry right now. Now I would like to call upon Dr. Sudhir Ranjan Jain for the concluding remarks.
All right. I must say good afternoon, good evening, and thank profusely all the brave people who are still here. It has been a fantastic day. Starting with the discussion, and all these talks have really shown a way why quantum computing and how quantum computing can change our lives. If I go in order, we see Jens Koch with his talk on superconducting qubits, which is the platform used right now by Google and IBM, and it's important. It's playing a very interesting role. Then we have also talked about fundamental questions. Sandeep Trivedi has been kind to give an overview, basic introduction, teaching us quantum physics. In short, entanglement, superposition ideas, and showing how they are connected to interesting quantum information questions, not only in computing, but also with black hole physics. we had an interesting, very fascinating discussion by Benoit Gremot on various aspects on topological phases of quantum matter and how ideas of topology come intersecting with properties of matter, phases of matter, new phases of matter, and even the braiding properties of identical particles in 2 dimensions contributing to computation paradigms which can protect and make a computation immune from errors. We had a very beautiful and long discussion and presentation by Professor Umakant Rapol, who has made pioneering contribution in the national context in building quantum computing labs where qubits and gates are practically developed. I have a personal request to Umakant that our students will visit your lab and should experience what it means to make a lab from scratch to how it stands today. And I hope these things will go a long way and inspire all of us. Professor M.S. Santhanam has always been very kind and willing to help us with all aspects of he was here for the teachers training program. We have very beautiful blackboard lectures. Now today, not blackboard not available, but but still quantum machine learning, very nice concrete examples with great clarity. Manoj Nambiar has always been, for some years, my old friend Anant Krishnan, I have to thank him. He mentioned that you have to call Manoj. All right. So I did that, and I'm doing that for a few years now. Every time I think of industry, I call up Manoj. Okay, can you help us with this? And he's always making very important contributions with his time and his expertise. I hope I'm not missed anybody. And I have to thank the audience who has been very kind. Our volunteers, our faculty members have done a fantastic job. The School of Engineering has shown great initiative. The Department of Information Technology, its head, deputy head, different heads of the departments, directors of different schools, the vice chancellor, everybody has been very willingly participating into this. So with this, I think we are done with the discussion of the dialogue, and I thank you all, and I hope that this becomes an annual event, and next year we should meet with Quantum Dialogue 2027 and compare notes, how far we have reached from today to next year. That would give us a real life line, how we are progressing. It is my pleasant duty to invite the speakers on the stage for the final act. I start with Professor Sandeep Trivedi, and I request Professor Irfan Siddhavatam so Come, you carry. Then Umakant, Professor Umakant Rapol. All right. Professor Benoit Gremot. And Professor M.S. Santhanam. Shri Manoj Nambiar. Thank you, Professor Irfan Sidhuvatam, for final 1 minute, out of which we have 52 seconds for the national anthem. And please, after the national anthem, I request all of you to join us for high tea.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे